Hello everyone, I welcome you all to the amazing platform of Physics Wallah English Wallah channel. Today we are here to discuss the new chapter which is the S block elements. Today we are here to discuss the one short lecture of this chapter with all of the important points covered in this chapter. Okay, so before starting this lecture, I want to discuss with you a very small and a very important thing. Like, we all have some goals in our life. We even have everyday goals. We even have goals which we will be able to accomplish in maybe 1 or 2 years. But what is required according to you to accomplish a goal? What is required? Like, I want to become doctor, maybe I want to become something else. The time is present. Like, if after 1 or 2 years I will be able to become doctor, I have a 2 years time right now. So what is required in that time to accomplish the goal? Okay, first of all, you should know your bigger goal, and then you should know the small steps to accomplish to that goal. Okay, that every small step you are taking, you should give your 100% in those steps. Those all 100% steps, those all small goals will combine with each other, and one day you will not even know that you have accomplished. When you will see at your back, you will see that you have accomplished so much. So always give your 100% in every of the tasks you do if you're moving towards the path of accomplishment of your goal. Because if we don't give our 100% now, you know when the results come, we regret so much, and that regret is something which does not let us live. We always, when we will be happy in after some or something like 1 or 2 months, but like sitting alone, we will think that, yeah, I did not even tried, I did not even give my 100%. If I would have been the best version of myself, if I have tried to give 100%, the things would have been better, the things would have been different. I would have been in the different phase. So we should not wait for that regret. Okay, we should always be the best version of ourselves. We should always give our 100% to every of the tasks we are doing, because the goals in our life is very very important. Without goals we are nothing. Okay, it's okay if you think that it's okay if I'm able to do, if I'm not able to, it's fine. Every people, every people are having different kind of mindsets. Some people are like, okay, should with everything, it's okay if I'm able to achieve this or not, it's okay, now let it be. But some people have the zeal. They by hook or crook or something, they want to be at that place. So they try the level best, they give their 100%. They just try to become the best version of yourself. You have to be that respective person. Okay, you don't have to be the one which is okayish with everything, because okayish is a comfortable life, and comfortable life does not make you achieve anything. Okay, so you have to move out of your comfort zone. You have to study hard, you have to do the hard work, you have to do the smart work. It's not like if you're doing the hard work, you're studying for 9 to 10 hours back to back, and you're thinking that you will be able to achieve your examination. No, it's not correct, because efficiency for a person to sit is only for the 3 to 4 hours. It's okay, you can study for 3 hours, you can have a half an hour break, you can refresh yourself, and then you can go back to study. It's okay. If you're not liking, if you're not in the mood to study sometimes, है ना, still you are opening the book, है ना, and you are studying. That book is reading something, you are also reading the book, but you are not able to understand the simple meaning of that line, because your mind does not want to study at that time. I know some people are present that they will say, ma'am, it happens to us almost every time, so what should we do? See, you are having very few days left for your examination. Okay, so you have to think in such a way, I have to study my level best, my 100%. I have to be the best version of myself in these days. I should not regret later that I did not even try. Okay, so with this promise, I want to take from all of you that you will be in the remaining days the best version of yourself. You will try the 100%. You will study all the lectures. I'm not telling you to study from the this place, that place, here and there. No. Right now, you people know everything, almost everything you people know. Just go through these lectures, just solve all the DPPs, just solve all the PYQs. It's okay. That much is required right now because few days are left to the examination and you have studied almost everything. Now this crisp one shot lectures and this questions, I have given like 50 questions in the chemical bonding. Okay, other teachers have given so many questions also, they have also given some so try those questions, solve those questions, just see that in which question you are facing a problem. Okay, it's not required right now that you're solving number of questions right now 100, 120. No, just pick your weak points right now. That if in the molecular orbital theory, ma'am, I was not able to calculate the bond order, I am facing problem in the bond order, so go to that portion, remove that weakness from your part. Okay, if you don't know the bond order, you're solving 100 questions from the molecular orbital theory. What is the need? It's okay, that is also required, but what if the question from the bond order is coming then? If you're doing a topic, please do it 100%. If you are touching molecular orbital theory, just make a promise to yourself that if a question is coming from the molecular orbital theory, I would be able to solve. If a question is coming from the bond angle, I would be able to solve. I have given you every of the required tricks in the chemical bonding in the periodic table. Just go through them. All the teachers have given you the best tricks. Just go through them and take the best version out of that. Keep that in your notes, keep that in your mind, and you will be like, I don't know what, you will be like the fire. Okay, so I think you people have understood what I want to say. Just one line, just be the best version of yourself in these coming days. Okay, just do your 100%, the 100% hard work. Okay, thank you so much for listening to me so calmly, so patience. Okay, you people are not present, but I can see you all. Okay, thank you so much. Now let's start with the lecture. Today we have to start the one short lecture of the S block elements. It's a very small chapter, and yes, it's important also. Some very different unusual orders you have to understand, so many new things you will get to know. So let's start the chapter. This chapter totally I will teach you with the help of the pen, because I think that is something which connects us more, right? So let's start now. Starting the chapter, S block elements. Now I'm starting the chapter which is S block elements. Now first of all, I want to know from all of you, what do you define the S block elements as? How do you define the S block elements as? Elements, you will write over here, elements in which last electron enters the S subshell, in which the last electron enters the S subshell. That will be called as the S block element, right? Its general electronic configuration. Its general electronic configuration is equal to NS122. We can write over here that whenever we have the NS1, we call it as group 1, and whenever we have the NS2 electronic configuration, we call it as group 2. So first of all, we have written what are the S block elements, what are the general electronic configuration for the group 1, for the group 2. Okay, in the periodic table, the group 1 and group 2 constitutes actually your S block elements. Okay, group 1 and group 2 constitutes your S block elements. Group 1, if you see, they are called as the alkali metals. Group 1, if you see, they are called as alkali metals. What are alkali metals? That are the bases that dissolve in water. So they are called as alkali metals. And what about the group 2 elements? They are called as alkaline earth metals. They are called as alkaline earth metals. Group 1 and group 2. And what is the meaning of the alkaline earth metals? They are simply alkaline and mostly found from the earth crust. So alkaline earth metals and alkali metals is the meaning of these two words. Not required, not asked, but you should know all these things, right? Okay, now let's move forward. Now we should know first the names of the elements of the total S block elements. That is, if I talk about the group 1, if I talk about the group 1, so what all elements are present? I have over here lithium, sodium, potassium, rubidium, cesium. We have all of these elements present. Lithium, sodium, potassium, rubidium and cesium. And even you can have the francium. See, francium is a radioactive element. We don't study much about the radioactive elements because they are not easy to handle. We are not knowing the much properties of these elements, okay? So they are present. This is present in the group 1, but we don't study in for the examination point of view, okay? So what is the general electronic configuration? You know that it is NS1. So it will be helium 2s1. Then we have neon. Then we have argon. Then we have krypton. Then we have xenon, and then we have radon. So these are the noble gases associated with all of these elements. Then the electronic configuration will be 3s1, it will be 4s1, it will be 5s1, it will be 6s1, it will be 7s1. So these are the electronic configuration associated with the S block elements, and this respective element is considered as radioactive. This is considered as radioactive, not studied much. This is considered as radioactive. Now let's discuss about the group 2 elements also. The group 2 elements also, which are having the general electronic configuration as NS2. The general electronic configuration as NS2. Okay. So let's have a look all of these elements also. So the elements will be beryllium, magnesium, calcium, strontium, barium and the radium. These all are the elements present. So we will be having the electronic configuration helium, neon, argon, krypton, xenon and the radon. So the general electronic configuration will be over here 2s2, 3s2, 4s2, 5s2, 6s2 and the 7s2. So even here this respective radium, this radium is also considered as the radioactive elements. Even we don't study much about the electro positive element, which is radium, because it is radioactive. It is not very easy to handle. Okay, now if you want to know the tricks that how you are going to learn these elements, you are moving from top to bottom, so you should know that how to learn these elements also. So the trick over here is, I am writing the trick in Hindi. Okay, so you have to learn in Hindi. So the trick is beta मांगे कार, scooter, बाप राजी. It means that a guy is a child is present. He is asking his dad for the scooter and his dad allows him to buy. So beta मांगे car also, scooter, बाप राजी, that the dad admits him to, yes, you can buy. It's very strange, right? But it's okay. People right now allow their children to buy all these things, and when we were small, not at all. Okay, what about this? So we have लीला ने की रब से फरियाद. लीला ने की रब से फरियाद. Okay, so you have to remember लीला ने की रब से फरियाद. Faryad means remembering or calling. Okay, so this is the meaning. This is the way in which you have to learn first the elements, their electronic configurations, right? Perfect. Now let us move forward towards the other properties. Now we have discussed this. One thing more I want to discuss over here is that, sometimes they can ask you a question about beryllium. Beryllium is not considered as alkaline earth metal. It's not considered as alkaline earth metals. It is sometimes not considered as alkaline earth metal. Why? As its oxides are amphoteric. As its oxides are amphoteric. All the alkaline earth metals resembles themselves in the nature that they form the oxides which are basic. But beryllium is like Vibhishan in Ramayana. He does not want to form the basic oxide. It forms the amphoteric oxide, which is the behavior which is very different from all of the elements. So sometimes it can be asked that which of the following element is not considered as an alkaline earth metal. So you should know your answer will be beryllium. Your answer will be what? Beryllium, right? Now, we have to discuss some properties. Now we have to discuss the properties of these elements. Now, we have to discuss the properties of these elements. So, what all properties are associated? Now, let's discuss the properties. First of all, the property we have over here is the atomic size. What about the atomic size of these elements? Is there any exception, or the order we have to follow is just straight? So, talking about the atomic size, there is no exception or exceptional order in this respective, either the S block elements or the group 1 elements or the group 2 elements. So there is normal trend. Okay. So the first is lithium, sodium, potassium, rubidium, cesium. Whenever I will have any of the exceptional order, I will always put 2 star. It's a usual order. I'm not putting any star over here. You have to remember 2 star. If I'm putting somewhere, it's exceptional order. So exceptional order are mostly asked in the examination. So you will have a look over there that I have to learn them. I have to put more importance to it. So I think you people have understood. Okay. So this is the atomic size for the group 1, and for the group 2 we have beryllium, magnesium, calcium, strontium and barium. This is how the size of the group 2 is moving, okay, which is beryllium, and moving towards barium the size will increase. Now let us talk about other property. After atomic size, we can have a discussion over ionization enthalpy. Now what do you think that how the ionization enthalpy or ionization energy will differ for these two? Talking about the group 1 and group 2, let's discuss. Talking about the group 1, ionization enthalpy order is very normal, because you know that when you're moving from top to bottom, size increases, ionization enthalpy decreases, and the order is normal for the group 1 elements. So order will be like this: lithium, sodium, potassium, rubidium and cesium. And if I talk about the group 2, it will be beryllium, magnesium, calcium, then we have barium, and then we have strontium. So we have an exceptional order for the strontium and barium. It was expected that it should move normally from top to bottom. It was expected that strontium would come over here and barium should come over here, है ना? Beryllium, magnesium, calcium, strontium, barium. But there is an exception over here. So I am making 2 stars. So you will be having an idea that yes, I have to put more focus on this order. I have to remember this order very nicely. Okay. So we are done with the ionization enthalpy. Now let's discuss the third property, which is electron gain enthalpy. Electron gain enthalpy. Let's discuss now the electron gain enthalpy. Now let's discuss. See, Whenever you are moving from top to bottom, your electron gain enthalpy decreases. Now we have to discuss over here, when you are moving from top to bottom, when you are moving from top to bottom, you always know that your negative electron gain enthalpy decreases. Your electron affinity, your electron affinity decreases. You know all these things, right? You know all these things very nicely. So first, the order of the group 1 will be like this: lithium, sodium, potassium, rubidium and cesium. And if you talk about the group 2, it will be beryllium, then magnesium, then calcium, then strontium and then barium. Okay, if you talk about the electron gain enthalpy, the orders will be like this. I have written over here the order of the, these two are the orders of the negative electron gain enthalpy. You know that the meaning of negative electron gain enthalpy is exactly equal to electron affinity. What does that mean? That is a tendency to accept the electrons effectively. Here lithium can accept electrons very effectively as compared to cesium. Beryllium can accept electron very effectively as compared to the barium. This is the meaning of this statement. So you have to learn the orders of these two, and even you should know that group 1 is having higher electron affinity as compared to group 2. Why? Because the group 1 is having the general electronic configuration as NS1 and it is having NS2. It is already stable. It is already stable. So if any electronic configuration is present which is already stable, it does not want to accept electron. So if it will accept electron, it will become stable. It will become NS2. NS2 is already stable. If you want to accept electron into that, it does not want to accept. Okay. Always remember, for the NS2, their electron gain enthalpy is always positive, right? That means that their electron affinity, that means that electron affinity is low. It's very low. So you have to remember these 2 points also. Electron affinity very low. Electron gain enthalpy is positive. Positive means that they don't want to accept electron. What all elements were having the positive electron gain enthalpies? Noble gas, nitrogen and the alkaline earth metals. They don't want to accept electron. So you have to remember these orders about the ionization enthalpies, about the electron gain enthalpies, and let's discuss the other part now. Now we have the other property which is, hydration enthalpy. Now let's discuss about the hydration enthalpy. Now what all important questions can be covered in this respective topic, which is hydration enthalpy? Now understand. See, I have discussed with you in the chemical bonding that what is the ultimate requirement for an ion to undergo hydration, or what, or how do we decide that this will be hydrated more or this will be hydrated less? With the help of the charge by radius ratio, right? We have discussed all these things. So hydration enthalpy we have to discuss. You always know, you have discussed with me in chemical bonding. I have explained you in a very detailed manner, in the chemical bonding, that the hydration is directly proportional. It is directly proportional to the charge by radius ratio. Your hydration is always directly proportional to the charge by radius ratio, right? Okay. Now, if I talk about the group 1 elements, you always know that when you are moving from lithium positive, sodium positive, potassium positive, rubidium positive and cesium positive. Okay, when you are moving from top to bottom, your radius increases. Okay, so your charge by radius ratio. So your charge by radius ratio will decrease. Charge by radius ratio will decrease because charge is same for everyone. It is positive one. Okay. So we can say that hydration. So we can simply say that hydration will also decrease. Hydration will also decrease. So the order of hydration will be highest for lithium, then sodium, then potassium, then rubidium, and then cesium. This will be the order for the hydration for the group 1 elements. And similarly, if I talk about the group 2 elements, it will be same. Beryllium plus 2, you are moving from beryllium plus 2 to you have barium plus 2. So when you are moving from top to bottom, here also your radius will increase. Your charge by radius ratio, will decrease because radius is increasing, your denominator is increasing. So as a result, your hydration will decrease. So order of hydration will be highest for beryllium plus 2, then for magnesium plus 2, then for calcium plus 2, then we have for the strontium plus 2, and then we have for the barium plus 2. So this is the order for the hydration for the group 2 elements, and these two orders are very, very important. It is asked very much. Here we can say that hydration for the lithium is the highest. We can write over here that lithium positive over here is having the highest hydration. So therefore only lithium over here is having its salt in the hydrated form. Only the lithium is having the highest hydration energy. If I talk about the halides, the lithium only have the halide which is present in the hydrated form. Rest all of them do not have any halide which is hydrated. Remember this thing. Okay. If I talk about the alkaline earth metals, in the alkaline earth metals, see, beryllium usually does not form the hydrated halides. Okay. But rest of the elements do form. What are those? So we have to write over here. We have over here MgCl2, we have calcium chloride, we have strontium chloride, we have barium chloride. So all of these have water of crystallization associated with them. It is having 8H2O attached, it is having 6H2O attached, 6H2O attached, and the 2H2O attached. So if they are hydrated, they are more hydrated, so they will have the more water of crystallization attached to them. Now a question can come into your mind. That who will be hydrated more? If I talk about group 1 and if I talk about group 2, let's compare the group 1 and the group 2. What according to you will be more hydrated or less hydrated? Now let's discuss. Let's take an example that group 1 is forming the ion which is M positive and group 2 is forming the ion which is M plus 2. Okay, let's take it as lithium plus 1. Let's take it as beryllium plus 2. Okay, now if you compare the charge by radius ratio, so group 1 over here will have plus 1, group 2 over here will have the charge plus 2. So you are not knowing the radius. Obviously you are not knowing the mathematical value of the radius, but you know when you're moving from left to right, your size is getting decreased. So if this is 2, so this will be 1. Beryllium will have the smaller size as compared to the lithium. So the charge by radius ratio will be greater for the group 2 elements. You can simply say that the charge by radius ratio is greater for the group 2 elements as compared to the group 1 elements. That's why you are able to see. That's why I am writing over here. Therefore, salts of group 2 is more hydrated. Salts of group 2 is more hydrated as compared to group 1. So you have to remember this thing very, very nicely. As a result, you can see in the group 1 only the lithium chloride with the 2 water molecules is only hydrated, whereas in the group 2 magnesium, calcium, strontium, barium, All of them are hydrated. They have the halides in the hydrated form. Yes, water of crystallization are changing because when you are moving from top to bottom, your hydration is getting decreased. Okay, so if you're having more hydration, more water molecules will be attached to you. If you are having less hydration, less water molecules will be attached to you. Okay, now let's move forward. We are done with this topic, which is hydration. Now, after hydration, what is the next important thing? Now, the next important thing we have over here is the flame test. Now, the next important thing over here is our flame test. You know that the S block elements give some colors in the flame. What you do, you take a platinum wire, okay? You just roll the platinum wire from one end in the form of a spoon. Okay, you just roll in a way that if you take the salt from it, salt will not fall down. Okay, you will make the loop, you will make a shape of a spoon or whatever you want. Okay, then you will take the salt, you will take that near to the burner, you will put that salt into the flame. The flame will show some color, and the color will help us to decide which respective salt is present, which respective cation is present in this salt. Maybe lithium, maybe sodium, maybe potassium. How we will be able to decide? By looking at the color of the flame. Okay, now we will be discussing what color will decide which respective ion. Okay, now let's discuss flame test. So lithium, sodium, potassium, rubidium and the cesium. These all elements are present. Okay, and if you want to know the color, just have a trick, CYVRB. Now what are the colors associated? This is crimson red. It is crimson red. This is yellow. Crimson red, this is yellow. This is violet. This is reddish violet, and this is blue. So these all colors are associated with the group 1 elements. You can learn it by CYVRB, and you will be able to solve your questions. Okay. Now let's discuss about the group 2 elements. We have beryllium plus 2, magnesium plus 2, calcium plus 2, strontium plus 2 and the barium plus 2. So if I talk about all of these elements, so we have a trick over here that first of all, beryllium and magnesium, they do not show any color to the flame test. But what about these elements? So I am writing over here the BCA. We have a course with us, BCA. So with that name, you can learn the name, which is brick red, this is crimson red, this is brick red, this is crimson red, and this is considered as apple green. Brick red, crimson red and the apple green. Now question arises that ma'am, why these beryllium and magnesium are not able to show any color in the flame test? You know, what is the reason for the color? If something is showing color, what is the reason, the basic reason responsible for that? You have studied the chapter structure of atom, in which we study two types of spectra: absorption spectrum, emission spectrum. What is absorption spectrum? There is a atom in which there is an electron. You give light to it. Light consists of 7 colors. Every color is having its own wavelength. Electron absorbs that light. Absorbing light means it is absorbing one of the wavelength of all 7 colors, and it will get excited to some higher state. Okay. Now the spectrum you are obtaining as a result will be absorption spectrum. All of the colors will be present. There will be one black line or whatever black line. Black line tells us about that this respective line, this respective value of wavelength is absorbed by the electron and it has moved to the higher state. Okay. Now you know that the electron is not stable at the higher state. It will come downwards. Okay. When it will come downwards, it will emit energy. Right. When it will emit energy, it will respectively emit that respective wavelength which it has absorbed. Okay, it is not stable at the excited, so it will come down, it will emit the respective wavelength, and that wavelength we will see on the spectrum. So that will be called as the emission spectrum. So we will see some color contrary to what which is absorbed. Okay, so now beryllium and magnesium are not showing the color because the basic requirement for the color is that electron should gain energy and it should move to the higher state. Beryllium and magnesium are small in size. The nucleus is attracting the electron of the beryllium and magnesium very tightly towards the nucleus. So if you're applying the energy, its electron is not getting excited and it's not moving to the higher state. That's why we are not able to see any color in the case of the beryllium or the magnesium. Okay, so we are writing over here beryllium and magnesium do not show beryllium and magnesium do not show any color to the flame test. They do not show any color to the flame test, and the reason for this is you know that due to very high ionization energy. If you want to know the reason also, reason, high ionization energy, electron can not be excited to higher level. Electron cannot be excited to the higher level. So you have to remember the reason. You have to remember the reason very nicely. You have to remember the reason very nicely. You have to remember that what all elements does not show the flame test. Okay, I think we should move forward now. And these are the colors of the flame test. Okay, now let's move forward. Moving towards the next thing, we want to know right now what about the photoelectric effect. What about the photoelectric effect? What about the photoelectric effect? Now, you know, you have studied the photoelectric effect in the chapter structure of atom. There is a tube in which electrodes are present. That electrodes are made up of the metals, and the metals used in that respective electrodes are from the alkali metal. So we can use the electrode of the metal, maybe sodium, maybe potassium, maybe rubidium, or maybe cesium. Lithium is not used. Lithium is never used. You know that during the photoelectric effect, we have this kind of a tube present with us. Okay, we have this kind of a tube present with us in which we have electrodes over here. Okay, we have electrodes over here. These electrodes are made up of metal. These electrodes are made up of metal, and that metal is maybe sodium, maybe potassium, maybe rubidium, and maybe cesium. And you should remember that cesium is mostly used because it is having the lowest ionization energy. Because you know, when the white light strikes the surface of this electrode, when the white light strikes the surface of this respective electrode, white light strikes the surface of this electrode, the electrons are coming out. Okay, photon is striking the surface of the electrode. Photons transfer its energy to the electron. Electron just move away from the electrostatic interaction of the nucleus, and it moves out from the surface of the electrode. If the energy you require for the removal of the electron from the metal atom is very, very high, okay, so the electron will not be out. Okay, so lithium here we cannot use because photon is having very high energy. That is true, it will go to the atom. Okay, what happens over here is, what happens, this is a metal. Okay, metal is having atom over here. Okay, atom is having the nucleus and this outermost electron. Okay, white light is coming over here. White light is having packets of energy. Every packet of energy is containing a photon. Photon strikes on the surface of this respective metal atom and it supplies its energy to this outermost electron. Now, if the binding energy, if the force of interaction between the nucleus and this respective outermost electron is very high, the binding energy is if very high, so this electron cannot move out. If photon is not having the sufficient energy to release, to overcome the force between the nucleus and the outermost electron, electron will not move out. So lithium cannot have this kind of a effect because ionization energy is very high. Because ionization energy is very high, the binding energy between the nucleus and the outermost shell electron is very high. So lithium can never be used in the photoelectric cells. Cesium is mostly used. And if you want to know the lithium, lithium can be used, you can use lithium can be used in the electrochemical cell. Lithium can be used in the electrochemical cell. Lithium can be used in the electrochemical cell, but not the photoelectric effect diagram, the setup, the electrodes. Okay. Now let's move forward towards the next step. We are not using alkaline earth metals over here. We usually use the alkali metals because the ionization energy of alkaline earth metals is greater than alkali metals. Okay. Now let's move forward. Now another thing we need to discuss over here is their reducing nature. Now, what do you understand by the reducing nature? That means you are behaving as a reducing agent. Reducing nature means that you are behaving as a reducing agent. That means you are reducing someone else, you are oxidizing yourself. It's okay. If you are talking about the reducing nature, that is very true. That self-oxidation is there and others, reduction is there. And according to you, what is oxidation? Oxidation is the removal of electron. So if that removal of electron is easy, you will be behaving as a very good reducing agent, and if the electron removal is hard, you will be behaving as a poor reducing agent. So according to you, if I see lithium is having the smallest size, its ionization energy will be the highest one. It will require very high amount of energy to oxidize itself. So it will be the poorest reducing agent according to you. Okay. So order according to you should be lithium, then sodium, then potassium, then rubidium, cesium. But this is not correct. Actually, the order of the reducing nature, reducing agent capability will be like this. For the group 1, it will be first lithium, then cesium, then potassium, then sodium. This is the order. Rubidium, I think I have missed over here. Rubidium, potassium, and the sodium. So this is the order we are getting over here. It's okay. The order is very true for all of these elements, but why lithium is coming over here? Lithium is having the very high amount of ionization energy. It is coming at the first place. It is telling us that lithium is behaving as the best reducing agent. That means it is oxidizing itself in the very best way manner, very easily. But it is practically possible? No. Ionization enthalpy are not like this. So there is something else which decides the reducing nature. It's not only the ionization enthalpy. Okay, there are some other factors also. Okay. So first of all, this we need to understand. And if you want to know the order for the group 2, and if you want to know the order of the group 2, so it will be like, first of all, barium, then strontium, then calcium, then magnesium, and then beryllium. They are having the normal order, but the group 1 is having very much exceptional order, and I have put a 2 star over here. So the exception is only present with the lithium, not with the other elements. Exception is only present with the lithium, not with the other elements. Okay. Now what is happening over here? What is the reason responsible for this? Now understand. See, always remember that reducing nature or ability to reduce other or ability to reduce others or ability to reduce other does not solely depend upon how easily you can oxidize yourself. It actually depends upon the three factors. Depends on first of all sublimation energy. First of all, it depends upon sublimation energy. Then next it depends upon ionization energy, sublimation energy, then we have the ionization energy, and then we have the hydration energy. Expected answer should be cesium, but it is coming lithium. So sublimation energy. Okay, what do you understand? What is happening in the case of the sublimation? What is happening in the case of the sublimation? You have a element M, solid. It is getting converted into M gaseous. Then we have M gaseous over here. It is undergoing ionization to release one electron. Okay, because you are reducing someone else, you are oxidizing yourself, and then in the third case, this M positive gaseous will be converted into M positive aqueous. So some energy will be released. This respective energy will have the value being positive. Even you have to supply energy to remove a electron. But if you are converting yourself from the gaseous to the aqueous form, energy will be released. Always hydration energy is released. Okay, now whenever you have to talk about the reducing nature, it depends upon the sum of, sublimation, ionization and the hydration. It depends upon the sum of sublimation, ionization and the hydration energy. The one which will have the greater value for it will behave as a best reducing agent. Okay, now it's very true that the ionization enthalpy of lithium will be very high as compared to cesium, but the hydration enthalpy of lithium will be very high as compared to the cesium. It will be very high as compared to the cesium. So if the ionization energy is high, it will be compensated by the hydration energy. So the overall sum will be greater as compared to lithium for the cesium. The overall sum will be greater for the lithium. This overall sum tells us about the E naught oxidation potential value. It tells us about the E naught oxidation potential value. That tells us that the oxidation will be favorable for the lithium as compared to the cesium. Okay, so you have to remember this thing. Do not think that it solely depends upon the ionization energy value. No, it's incorrect. It depends upon the sublimation also, ionization also and the hydration also. So you have to remember this thing very nicely. Okay, so if you are having this respective order, that cesium, rubidium, potassium, sodium, it's fine. When you're moving from top to bottom, you are having the your ionization energy is getting decreased, so cesium will have the very less ionization energy. But lithium is coming in the front because we never take the only ionization energy value, we take the whole of the three values, and for that lithium positive is having the very hydration energy value that is compensated for the ionization energy. But in the case of the group 2, there is no exception. We are just following the simple trend. Okay, so always remember that this we are following, and whenever we talk about the reducing agent and the oxidizing agent, we usually talk about in the aqueous solution. We talk usually in the solution form. If you are talking about in the gaseous form, then the reducing nature will be totally depending upon the ionization energy. That is not depending upon the sum of the three values. So whenever we take the solution form, we have to take the E naught potentials, and that depends upon the sublimation, ionization and the hydration. So here we are talking about the solution form. Here we are talking about the solution form. Here we are talking about the solution form. So remember this thing very nicely. Now let's move forward. Now let's discuss more about the elements which are radioactive. In these S block elements, what all elements are radioactive? First of all, you have to tell francium and the radium. What element can form gaseous element? Gaseous element. That does not mean that the element is gaseous, but this hydrogen actually exists as H2, so it is considered as the gaseous elements. It's okay that hydrogen is anomaly where it should be present. It should be present with the S block elements or the group 17 elements. Right now we are considering in the S block elements, so we are talking it as the uh, gaseous element because its atomicity is 2, it behaves as the gas. Okay. Now if you want to know the element which has a very low melting point, that will be cesium and francium. They are having a very low melting point in this respective group, which will be the alkali metals and which will be the alkaline earth metals. Okay. Now let's move forward. Moving towards the next property, the next property which will be having is density. The next important property we need to discuss over here is the density. So whenever you are moving from top to bottom, you will think that the usual order for the density should be moving from top to bottom, your density should increase. Okay. So you should have the order for the group 1. You will think that, ma'am, lithium, then sodium, then potassium, then rubidium, and then cesium. This should be the order which is you are expecting. But as usual, we have a inorganic chemistry. We always get some exceptional answers. So lithium, then potassium, we are having sodium, then we have rubidium, and then we have the cesium. Top to bottom, yes, your respective density is getting increase. That is very true. When you're moving from top to bottom, your density is getting increased, but there is an exceptional order in the case of the potassium and the sodium. We have to remember that potassium is lighter than sodium. Potassium is lighter than sodium. Potassium is lighter than sodium. Always remember. And that is explained with the help of the volume values. The volume values of the potassium is exceptional. That's why we are having this exceptional trend. Okay. Okay. Now we talk about the group 2 elements. What about the group 2 elements? Then we have the order will be like this. And what you are expecting, the order is not exactly like that. Order is very exceptional. The order is very exceptional. So how we are going to learn this respective order? I'm writing a trick over here. Just remember that trick. Okay. The trick is बाप के सर पे बेटा मांगे कार. Okay. There is a child who is actually forcing his dad that he wants to buy a car. So he's sitting on the head of his father and he's just asking and asking and asking that I want a car. So बाप के सर पे बेटा मांगे car. So this is how you have to remember this. Okay. So don't laugh and just remember. Okay. This is important for the examination point of view. Okay. So jokes apart, let's move forward. Next we have over here is our melting point and the boiling point. Next we have over here is our melting point and the boiling point. Now let us discuss first for the group 1. If I talk about the group 1, the order for the melting point and the boiling point is same, and the order will be melting point and order and the boiling point order is same, but the order is like this: lithium, sodium, potassium, rubidium, and the cesium. The order is like this. Okay. Now, why so? Because whenever we have a metals, we have a bond which is present over here is a metallic bond. Okay, we have a metallic bond associated with the metal. So when you are moving from top to bottom, the size of the metal atom is increasing. So the metal metal distance is also increasing. So the bond is becoming weakening. The bond is weakening. Okay. So very less amount of energy will be required to break that bond. Okay. So metal metal bond strength is decreasing from when we are moving from top to bottom. So the melting point and the boiling point will also decrease. Okay. Metallic bond. Okay, moving from top to bottom, your metallic bond weakens. So you don't have to write all these things. Nobody will ask you all these things, but you should know. As a knowledge, you can make a box on the right or left hand side of your notebook, and you should know the reason, right? Okay. I can simply write over here the reason as metallic bond weakens, metallic bond weakens moving from top to bottom, moving from top to bottom. Okay, remember this thing very very nicely. Now, but what about the order of the group 2? Now what about the order of the group 2? They are not having the similar order for the melting point and the boiling point. So first I'm writing over here the boiling point. So these are the order for the boiling points and for the melting point. So ma'am, this is a very exceptional order. Now what we have to do for this? First of all, I have to make a 2 star over here, so that you should remember that you have to learn these even more. Now, how? Beta बाप रोए कहाँ सर मारे. I think they have now the child is like, I want a car, and the father is saying it's okay. Now they went to a shop, they have bought a car, and the car is like very it's not having very good operations, its average is very low, and its working conditions are also not good. Maybe they have got into a trouble. Now what they are saying, बेटा बाप रोए कहाँ सर मारे, क्या करें अब. So बेटा बाप रोए कहाँ सर मारे. It's the way you have to remember the boiling point. Now the melting point. So this is the trick for the melting point. Now now they were very worried that what car we have bought now. They are very upset. Okay, so they are sleeping like in the night. Suddenly, the child asks his father something. Beta kahe suno baba raat mein. They are sleeping with each other. The child is suddenly he wakes up and he is pushing his dad that please wake up, please wake up. So what he is saying, beta kahe suno baba raat mein. So this is the whole story which is going on, the car and everything. It starts with the alkaline earth metal itself. So this story ends over here. With this respective trick, you have to remember the values of the melting point and the boiling point. So let's move forward with the other property. Now, moving forward, so we have discussed almost all of the properties, the physical properties, density, melting point, boiling point, photoelectric effect, and ionization energy, hydration, electron gain enthalpy. We have discussed almost everything, okay? Now we have to discuss the chemical nature also, that how they are chemically reactive. So let's start with the discussion. So we have to discuss now their chemical properties. We have to discuss now their chemical properties. Their chemical properties. Now we have to discuss their chemical properties. Now let's start. Now what is happening over here in the terms of the chemical properties? First of all, we have first of all, we have reaction with air. First of all, we have the reaction with air. See, so the air actually contains O2 and O2. It's okay, it contains many other things, many other species present, but right now we have to discuss only about the O2 and the N2. Okay. Now we have to totally discuss first of all about the group 1 elements. Group 1 elements. So we have what type of elements present with us? We have lithium, sodium, potassium, rubidium, and the cesium. We have all of these elements present with us. Now, we have different types of ions which are formed when the oxygen is actually reacting with the alkali metals. When lithium actually reacts with oxygen, it forms lithium oxide. Okay, this sodium forms sodium peroxide, whereas the potassium forms potassium superoxide, rubidium forms superoxide, and the cesium forms superoxide. Now by looking all these structures, you will not be able to identify in the one go that how ma'am is calling oxide, peroxide, or the superoxide. So you should know the ions. You should know the ions associated with them. Okay. So when I'm breaking them, I'm going to get lithium plus 1 and I'm going to get O2 negative. So this respective ion, the single oxygen ion which is having the 2 negative charge, is the oxide ion. Okay. Now the sodium is 2Na positive plus O2 2 negative. This ion which is present over here is called as the peroxide ion. Whereas the potassium will be O2 negative, cesium will be O2 negative, and this rubidium will be also O2 negative. So all these three forms I will write over here only. This respective is forming oxide. This is forming an oxide. This is forming a peroxide. This is forming a peroxide. And all these three are forming the superoxide. All of these three are forming the superoxide. All of these three are forming the superoxide. So we should know first which is forming oxide, which is forming peroxide, and which is forming the superoxide. First we should know all of these things present over here. I have written all of these. Now see, it's not a necessary condition, or it's something compulsory that lithium will form only oxide or potassium will form only superoxide. If you go to a foreign writer, or practically if you see, every element can form every of the oxide, peroxide, or the superoxide if we change the conditions. But we have to follow the NCERT, and according to that data, what is written on the blackboard, you have to go according to that only. Okay, remember this thing. Okay, so these are the elements which are forming these kinds of a thing. Now let's discuss about the one more thing I want to tell you is, let's also discuss over here about one more thing. Even the air contains, the nitrogen also. So only lithium reacts with N2 to form Li3N. Only lithium. I should always, I should not write this reaction like this over here. I will write for the N2. Okay. Reaction will be M plus N2 is giving you M3N. But this M is only and only lithium. There will be no alkali other metal present over here which is going to form a nitride, which is going to form a nitride. Only lithium. This is called as a nitride. Why it is called as a nitride? Because it is having N3 negative ion attached with it. So this N3 negative ion is associated with the name called as the nitride. So only lithium will form. Now after that, let's discuss about the group 2 elements. Now let's discuss about the group 2 elements. So for the group 2 elements, we have beryllium, we have magnesium, we have calcium, we have strontium, and we have barium. We have all of these elements. Okay. Now we have all of these elements. Now if you say beryllium forms beryllium oxide, this is forming magnesium oxide, calcium oxide, strontium, and the barium. But what about the formulae? What exactly they are called? What exactly they are called? How they are dissociated? Beryllium is dissociated as +2, whereas O2 negative. Magnesium as +2 plus O2 negative. Now calcium as +2 and it is having the O2 negative ion. Strontium as +2, it is also forming a peroxide ion, whereas barium as +2 also forming the peroxide. And you must know very, very nicely in your head, you all have to keep this thing very clearly that these two are going to form oxide. These two are going to form the oxide, whereas all these three are going to form the peroxide. They do not form any superoxide. For the formation of the superoxide, we have the greater oxygen content, and for that we should have a greater size. So only in the alkali metals we are able to see some of the elements which are forming the superoxide, but you know that the size of the alkaline earth metal is less, so they are not able to form any kind of a superoxide. Now what about the nitride in the case of the alkaline earth metals? Now what do you think what they will do? If you talk about the alkaline earth metals, okay, if I talk about the reaction with N2, so M reacts with N2 to form M3N2. Now this is also a nitride, okay, it will break in the form of M plus 2 N3 minus. Even it is also called as a nitride, but M is all elements, all alkaline earth metals form the nitride. All alkaline earth metals forms the nitride. If you take beryllium, magnesium, calcium, strontium, barium, everybody of them forms the nitride. So this is the first what you are going to get when you are reacting alkali metals or the alkaline earth metals with the oxygen. Okay. Now let's discuss about these ions present. Okay. We have over here this oxide ion, we have over here this peroxide ion, and we have over here this superoxide ion. This ion will be called as oxide ion. This ion will be called as oxide ion. This will be called as peroxide ion. This ion will be called as peroxide ion, and this ion will be called as superoxide ion. Okay. So first we should know the names of all of these ions. First we should know the names of all of these ions. Okay. Now let's discuss about the other properties. That is, oxide ion is a monoatomic ion. It is monoatomic ion. This whenever reacts with water, it is going to get a hydroxide. It is going to get a normal hydroxide. Let's say for example, if I react lithium oxide with water, I am going to get simple lithium hydroxide. I am going to get simple lithium hydroxide. Now what about this? This is a diatomic ion. This is a diatomic ion, and with the help of the molecular orbital theory, I can call it as diamagnetic. If you'll draw the MOT diagram of O2 negative, which I have already told you in the chemical bonding chapter, I have told you how you have to draw the molecular orbital diagram. So there you can calculate that it is coming out to be diamagnetic, and this is something very, very important. Okay. Now what happens when you react this O2 negative with water? You are always going to get this hydroxide ion, and along with that you are always going to get the H2O2 also. Now let's say if I take sodium peroxide and I react that with the water, I'm going to get sodium hydroxide plus H2O2 always. I'm going to get this sodium hydroxide and the hydrogen peroxide always. Okay. Now superoxide ion. This superoxide ion is also considered as the diatomic ion. With the help of the molecular orbital theory, it is always considered as the paramagnetic because there is only one negative charge. So there will be one electron which will be present unpaired in the pi star 2py orbital. Okay. So you will be having the nature as paramagnetic, and if you react this with water, you are going to get a hydroxide plus you are going to get H2O2 and plus you are going to get the O2 as the product. Okay. Now what you are having over here is, as an example, KO2 reacts with H2O to give you KOH plus H2O2 plus O2. Okay. KOH plus H2O2 plus O2 will be the product. So these are the products associated with the oxide ion, peroxide ion and the superoxide ion. This is something very, very important. This is something very, very important, and you should know all of these very, very nicely. Oxide, peroxide and the superoxide. Okay. Now I want to tell you one more thing. Now I want to tell you even one more thing, that is with respect to the sodium. You know, when sodium actually reacts with O2, when O2 is in the less concentration, or it is limited, or it is in the higher concentration, when it is in the less concentration, it forms Na2O2, which is peroxide, but if it is in the very high concentration, it forms the sodium superoxide compound. And this Na2O2 is having the name which is called as solo zone. It is also called as solo zone. It is also called as solo zone. And even I will tell you one more application. This respective sodium peroxide and this respective potassium superoxide are used in submarines. This is something very, very important. It is asked, I don't know how many number of times this is asked. You know what happens if you react this potassium peroxide with the compound which is released as a result. Okay, the compound which is released as a result in the submarines, which is CO2. It actually reacts with CO2 to form the carbonate K2CO3, and it actually converts this respective CO2 into O2. This is a very beneficial reaction. This is considered as a very beneficial reaction under the submarine section, that CO2 is converted into the O2 with the help of the potassium superoxide. So this is something very, very important, okay, for the 1 star. That means you should remember it's a application, it's a use, sometimes it's asked also. So this is all of the things related to the oxide nature. With the reaction with air, I have discussed everything: peroxide, superoxide, application, and group 2 also I have discussed. So I have discussed everything with you. Okay, now let's move forward. Okay, now we have to discuss another thing, which is the reaction with water. Reaction with water. Now, whenever you're talking about the reaction with water, what is going to happen? Reaction with water. What is going to happen? Now, understand. Whenever you take any M element, either from the group 1 or the group 2, you react that with the metal, the water, you are going to get you are going to get a hydroxide, maybe you are going to get MOH, okay, or maybe you are going to get MOH whole twice. It can be with respect to the M being alkali metals. See, M can be anything. M can be either alkali metals at, or it can be alkaline earth metal. If it is alkali metal, it will be M plus 1, or alkaline earth metal, it will be M plus 2. So you will be having this, है ना? You will be having one electron released over here, you will be having two electrons released over here. So you will form a hydroxide, and that also with the release of the hydrogen gas, okay, that also with the release of the hydrogen gas, okay. Now this is perfect. Up, now what you have to remember when you are talking about the reaction with the water, remember this thing, that reaction of alkali metals with water is considered as highly exothermic. Question is being asked from the group 1 only, okay. They are highly exothermic. You know, the reaction depends upon the actually the melting point. When alkali metal reacts with water, that reaction is highly exothermic. It is a vigorous reaction, and the reaction order which is reacting in the more vigorous way, so the cesium, then rubidium, then potassium, then sodium, and the lithium. So lithium is reacting in the very normal way, but the cesium when reacts with water, it almost very highly vigorous. They, this respective cesium to sodium, these elements when they are reacted with water, when they are coming in the contact with water, they catch fire. Now why do they catch fire? Now understand, these all elements, I'm writing over here, these all elements, reaction highly vigorous. I'm writing over here that reaction over here is considered as highly vigorous. Reaction over here is considered as highly vigorous. They catch fire. They catch fire in contact with water. In contact with water. Whenever a metal actually reacts with water, what is happening? Let's say I have a beaker. I have put it a metal over here. Now this surface of the metal is coming in contact with the water. There is a very small piece of metal. I am having this surface of the water, and this is present on the surface. I'm just putting this metal over here. Now what happens? Whenever metal reacts with water, the reaction is exothermic. Some heat is evolved. That heat is sufficient to melt the metal. When the metal is melted, okay, so it will increase its surface area. Let's say it was like that, it will start increasing its surface area. It will start increasing its surface area because the reaction is exothermic, heat is getting involved, okay. First only this part was coming in the contact with the water, okay. This much heat was evolved. Now more is coming in contact with water, more heat is evolved. More is coming in contact with water, more heat is evolved, and ultimately this much heat actually is shown in the form of the fire. It comes out in the form of the fire. We look at that metal in the water, and we are able to see that there is a fire present. Now why some of the metals we are able to see that the fire is there, while if lithium is putting in the water, there is no fire? Because the problem is, if this metal is having a very low melting point, है ना? So that respective heat which is coming out, so the reaction is exothermic now, it is evolving heat now. So metal, if it is having a very low melting point, it will get melted, it will have a more surface area in contact with water. But if the metal is having very high melting point, it will not be melted, it will remain like this only. It will remain like this only. This area coming in contact with water will not increase, so the reaction will be very less exothermic. It will not be seen as the fire, okay. So this all problem depends on the melting point of the metal. If the melting point of the metal is very low, so the metal can catch fire easily. And you know that when we are moving from top to bottom, our melting point and the boiling point in the case of the alkali metal is decreasing. because you know that the metallic force is decreasing, metal bond length is increasing. As a result, we are able to see this. Okay, I hope you people have understood. I just want to have the order which is present over here. You should know that they catch fire when they are put it in the water, but lithium does not, because it is having the very low melting point. It is having the lowest melting point. I have explained you the whole concept. They will never ask you the reason for it, but you should know the reason. That's why I have told you, but they are not going to ask you the reason. Okay, now let's discuss the next part, reaction with water. Now let's discuss reaction with liquid ammonia. Now let's discuss reaction with liquid ammonia. And before that, I want to even discuss with you one more thing. I want to discuss with you one more thing. That is, this is only for the case of the alkali metals. If I want to tell you something about the alkaline earth metal, so you should know that beryllium rarely reacts with water. Rarely reacts with water. It is having a very less reactivity with the water, almost negligible, almost negligible. Magnesium reacts, but it only reacts with the hot water, whereas the calcium, strontium, barium, they can react with the cold water. They don't, these elements actually, they don't react with water, but if you want to know the critical conditions in which they react, you should know. Even one more thing I want to tell you is that, even one more thing I want to tell you here is that, always remember, always remember, always remember that for reactivity, always, whenever you have the reactivity order, always remember that it is greater for group 1 as compared to group 2. It is always greater for group 1 as compared to group 2. But why this is so? Because reactivity, because reactivity is inversely proportional to ionization potential. You know that group 1 has less ionization potential, they are more reactive, and group 2 has more uh, group 2 has more ionization potential, so it is less reactive. It is less reactive. You should know all of these things very nicely. This will able, it will be able, it will make it easier for you to understand what is the problem over here. Why alkali metals are more reactive towards water, alkaline earth metals are less reactive towards water. One is reacting in the cold condition, one is reacting in the hot condition, one is not at all reacting with water. So this is the reason. Okay, I hope this is clear to everyone. Now let's discuss the reaction with liquid ammonia. Now we should move towards the reaction with the liquid ammonia. Now you know, whenever the metal of alkali metal or alkaline earth metal, whatever you take, first I am explaining with respect to the group 1 elements. First I am explaining with respect to the group 1 elements, and I am telling you the question is asked from this chapter in the solution of the liquid ammonia from the group 1 elements only. So focus on that. It is not asked in the case of the group 2 elements. So focus on the group 1 elements. Okay. Now what is happening? You take a metal, you react that with the ammonia, and ammonia you are taking is a number over here which is x plus y. I will tell you what is the number of x, what is the number of y. I will tell you over here. Okay. So you have a metal over here, you have ammonia over here, and this much number of molecules are surrounding, whereas here you have electron over here and ammonia over here with a y, and this much number of ammonia molecules are surrounding the electron. So here we call it as, here we call it as, here we call it as something which is ammoniated metal. We call it as ammoniated metal, whereas we call it as ammoniated electron. Ammoniated metal and ammoniated electrons. That means metal is surrounding some ammonia molecules. Okay, some ammonia molecules, and those number of ammonia molecule is considered as X. Similarly, if we have the electron in the middle, ammonia molecules are surrounding the electron also, and those all will be considered as Y. So ammoniated metal and ammoniated electron is present. Okay. Now there are some of the questions which are asked from this respective reaction first of all. Okay. When you have concentration which is less than 3 molar, when you have the concentration less than 3 molar, it is asked that this solution is paramagnetic. So why this solution is paramagnetic? First of all, this respective solution is in the color which is blue. Why this solution is in the blue color? And why this solution is having the reducing nature? Why this solution is having the reducing nature? And why this solution shows conductivity? Why this solution shows conductivity? So first of all, we have to answer the reasons of all of the four properties. What in these two are responsible for these all four properties? Okay, so the paramagnetic nature, the blue color, the reducing nature, all of them is due to ammoniated electron. The ammoniated electron is responsible for the paramagnetic behavior. You know, whenever you are having the paramagnetic behavior, you always see the unpaired electron. Whenever you have a reducing nature, you have to give electron and then you will be reduced. Okay. And color is always responsible because of the presence of the unpaired electron. So color is blue. Okay. So all of these three properties are because of the ammoniated electron present over here. But the conductivity is due to ammoniated metal plus ammoniated electron. It is due to ammoniated metal plus ammoniated electron. Both of these, because you know conductivity is due to the positive ion also and due to the negative ion also. Both of them are responsible for the conductivity. Even the metal positive and the electron, both of them are responsible for the conductivity. So please remember this thing very, very nicely. And let's say if I take concentration greater than 3 molar, if I take concentration greater than 3 molar, then the things will change. Then the things will change. Now the solution will become diamagnetic. Now the solution will become diamagnetic. Solution will have color changing from blue to the bronze. The solution will have the color changing from the blue to the bronze, because whenever the solution is of no use, you know, whenever the concentration is very, very high, if you let the solution stand for some time, its concentration will increase. Okay, so the metal will start forming the clusters. That clusters will make the solution of no use. The solution will be of like no importance. It will change from its color from the blue to the bronze. Okay, it will be of the no use. Okay, you know, when something is of no use, or something has reached to the condition which is very bad, we always visualize the color as the brown or the bronze colored. So you should remember, concentration greater than 3 molar, the solution is of the no use because of presence of the metal clusters, and the diamagnetic nature also is the result of those metal clusters. Okay, now even they can ask you, if the solution withstand, if you let the solution withstand for some time, okay, so what will be the result? This M metal reacts with ammonia in that case, and you are going to form metal amide plus hydrogen gas. Now how you are going to get this? This respective metal will break into M positive plus electron. This will break into NH2 negative plus H positive. So this M positive combines with the NH2 negative to form MnH2. This electrons combines with the H positive to give you H, and another H combines with the H to give you hydrogen gas. So this is the metal amide plus hydrogen gas evolved. Metal amide plus hydrogen gas will be evolved in this respective case. So sometimes a question has come in the JEE mains about this reaction. A question has come in the JEE mains about this reaction. When a metal is the metal stands in the solution of the liquid ammonia, will there be any evolution of the hydrogen gas? Yes, there will be evolution of the hydrogen gas, and you can see this from this respective reaction. Okay, so this is asked in the JEE mains exam, this respective reaction. Okay, so let's move forward to the other part. So we are done with the part of the reactions in liquid ammonia. We have discussed all of the important things, that at the normal concentration, what happens at the concentration greater than 3 molar, what happens, and when you let withstand the solution, what happens. Okay, so this is the case when you let withstand the solution. If you want to say that, ma'am, please write this also. So I will write over here, solution, if it is withstand, that it is kept for some time, so the equation will be like this. Okay, so let's move forward towards the next important portion, which is the reaction with the hydrogen. Now we are moving towards reaction with hydrogen. Let's move towards the reaction with hydrogen. Now what is going to happen when you are going to react alkali metals and alkaline earth metals with the hydrogen? Now let's see. Reacting M with H2 is going to get you either MH or MH2. These are called as hydrides. These are collectively called as hydrides. MH is formed by the alkali metals, whereas MH2 is formed by the alkaline earth metals. This is alkali metal and this is alkaline earth metal, but this M will not be the beryllium. Beryllium actually does not form the hydrides directly. They form hydrides, but that are formed indirectly, you should know. Okay, so how they are formed? I'm writing over here. Beryllium does not form hydrides. Beryllium does not form hydrides easily, or you can simply say directly, easily or directly. So what and how it is happening is, beryllium chloride reacts with lithium aluminium hydride to form BeH2 plus lithium chloride plus aluminium chloride. So this is how the beryllium hydride is formed. Okay, and always remember that the hydride of beryllium is polymeric. Okay, I should tell you that group 1 elements always form the ionic hydride. We have discussed in the hydrogen chapter, they always form the ionic hydride, whereas group 2 beryllium and magnesium collectively form covalent hydrides. They form covalent hydrides. Always remember this thing, that what are the properties associated with the nature being ionic or covalent. You can study them from the chapter which is hydrogen. I have explained them. Okay, so this is, you have to remember, you need to remember this very nicely. And even the question can be asked from the lattice enthalpy also. So the order of lattice enthalpy will be lithium hydride, then we have sodium hydride, potassium hydride, rubidium hydride and the cesium hydride. Because smaller the size, greater is the lattice enthalpy. You know that lattice enthalpy is directly proportional to the charge product and divided by the radius. This is lattice enthalpy order. Lithium hydride to cesium hydride. So always remember all of these things. Okay, we have discussed everything about the hydrides. You can go through the hydrides, how they are formed, group 1 elements, group 2 elements, and that's it. Okay, now let's discuss the other part, which is reaction with halogens. Reaction with halogens. reaction with halogens. Now, what is going to happen? You react M with X2, you are going to get Mx. You react M plus X2, you are going to get Mx2. Okay? Here M is your alkali metal, here M is your alkaline earth metal, but not beryllium. Same problem. Beryllium cannot even form the halides directly. Okay? The next step over here will be beryllium do not form halides directly. They do not form halides directly. First is the process ammonium fluoroberylate. It breaks to give you ammonium BeF2 plus HF. Ammonia BeF2 plus HF. And if you react BeO with CO, not CO, CCl4, it gives you BeCl2 plus CO. So this is how you are going to get the halide of the beryllium, which is not direct one. You have to react beryllium with some other thing in a more direct way, in a more indirect way. Okay? So this is how you have to undergo. Now one more thing which is important to understand in the case of the alkali metals, reactivity with the fluorine or the fluoride ion will be greater for lithium, then sodium, then potassium, then rubidium, then cesium, always. Okay, but for the case of the bromide iodide, the reactivity order is inverse. The reactivity order is inverse. Why so? Why is this case? Because you know that fluoride is a smaller ion. When it combines with a lithium, when a lithium which is also smaller in size, both small ions combines with each other to form a compound which is having a greater thermal stability, greater bonding between them, greater lattice enthalpy between them. Always remember, a small ion when combines with a small ion, their lattice is strong. Big ion, the lattice is strong. Big ion, smaller ion, the lattice is very weak. So always you have to use this basic concept of the chemical bonding in most of the concepts of the inorganic chemistry. So cesium is bigger, combining with a bigger ion, this is the thermal stability order and the reactivity order. Lithium combines with the fluoride more effectively because the lattice as a result forming the compound as a result forming is stable. Okay, so here we are having the reactivity order. Here we are having the reactivity order. Right? Okay. Now, talking about the halides, we have to discuss something important for the beryllium also. Beryllium halide, that is the chloride, exists in very different ways. That is, first way is in the form of the dimer. Other way, first the monomer, then we have the dimer, and then we have the polymer. I think the space we are using is not correct. First we should make the polymer. First we should make the polymer. This is the polymeric form of the beryllium chloride. Then we should make a dimer. And then we should make a monomer. These are the structures responsible for the monomer, for the dimer, and for the polymer. Okay. Now let's write about the properties of these. This is considered as the monomer. This is a monomer. It is existing in the vapor phase. This is existing in the vapor phase. This exists at a temperature around 1200 Kelvin. 1200 Kelvin. Here the hybridization is sp. The shape is considered as linear. So this is all which is present with the properties of the monomer of the beryllium chloride. Okay. Now this is considered as the dimer, and it is existing at a temperature nearly equal to 1000 Kelvin, and this is having the hybridization as sp2 and the shape being triangular planar. This is triangular planar. Okay. Now this is a polymer. Now this is a polymer. Okay. Exists at room temperature. This exists at room temperature. Hybridization being sp3, shape being tetrahedral, and this is considered as the polymeric form of the beryllium chloride. Okay. You have to remember the properties associated with this. If anybody is confused in the case of the hybridization, you can simply calculate the sigma over here. You can simply calculate the sigma and you will be able to calculate the hybridization. So sigma, number of sigma bonds, actually gives you the information about the hybridization. Okay. So these all things are important with respect to the reaction with the halogens. You are able to form the compound which is mx. You can form the compound which is mx2. And what is m? What is m in the case of this compound? We are not taking beryllium. Beryllium halide is prepared indirectly. What is the reactivity order? Reactivity order is basically asked for the alkali metals. If you want to have for the alkaline earth metal, that will also be the same. The smaller ion will combine with the smaller ion, the bigger ion will combine with the bigger ion. Okay. I hope this is clear to everyone. Now, we are done with the halides. Now what we have to do? Now we have to move towards a very important topic which is thermal stability. Which is thermal stability of the compounds. Thermal stability of the compounds of the S block elements. Thermal stability of the compounds of the S block elements. Now what is going to happen? Understand. Before understanding the thermal stability, let us first go through some concepts. Okay. Understand first of all, whenever we want to calculate the thermal stability of mono atomic anion, that is directly proportional to the lattice energy. And the lattice energy is directly proportional to the product of the charges and inversely proportional to the distance. Okay. Another thing which is, if you want to calculate the thermal stability of either polyatomic anion or diatomic anion, polyatomic anion and the diatomic anion, it is inversely proportional to 1 upon polarizing power of cation. Very, very important to understand. Very, very important to understand these two things. Very, very important to understand these two things. I hope first you are relating with me what I have written. polarizing power of the cation and lattice energy. Okay. Now I have to discuss with you. Now I have to discuss with you the polarizing power. Now I have to discuss with you the polarizing power. Please have a attention and listen to what ma'am is saying very carefully. Okay, listen to what ma'am is saying very carefully. Okay, so let's discuss about the polarizing power now. Now we have some of the categories present now. Now we have some of the categories present with us now. What are those categories? What are those categories? Let's say I have a mask in my pocket. Okay, so first of all, we have a electronic configuration which is considered as inert gas. So group 1 and group 2 cations are coming under this category. Let's say sodium positive, let's say magnesium plus 2, any of the respective ion which are formed from the group 1 or group 2 is considered as the inert gas configuration. Okay, then next we have pseudo noble gas configuration, and the next we are having over here is the pseudo noble gas configuration. What all ions are coming under this category? Coming ions are zinc plus 2, cadmium plus 2, mercury plus 2, copper plus 1, germanium plus 3, gallium plus 4, silver plus 1 and gold plus 1. All these are coming in this category of the pseudo noble gas. And then we have non inert gas configuration. And then we have non inert gas configuration. What we have? We have non inert gas configuration. Then what we have to do in this respective case? What we have to do in this respective case, which is the non inert gas configuration. The configuration, first of all, the ions will be lead plus 2, thallium plus 1, bismuth plus 3 and mercury. Electronic configuration associated with them is NS2, NP6. Here it is NS2, NP6 and ND10. Whereas here the electronic configuration present always will be NS2, NP6, ND10, N plus 1, S2. First you have to understand that what all categories are present. Non-inert gas, inert gas and the pseudo-noble gas. Okay. So in nutshell, you have to remember this trick that always the polarizing power, always this polarizing power is directly proportional to first the non-inert gas configuration, after that pseudo noble gas configuration and after that inert gas configuration. We have actually this order present with us: non-inert gas, pseudo-noble gas and the inert gas. The polarizing you can write just for a second. The polarizing power which is written in front of you is like this. Okay, we have to use this, है ना? I have written all of these things because I have to use it over here. I have to use this for the thermal stability of the polyatomic anion compounds. Okay, so first write all of these things. Okay, non-inert gas, pseudo-noble gas, and the inert gas. Now, I am going to ask you some of the questions. Let's say I have sodium carbonate and I have rubidium carbonate, and I want to ask you, is the least thermally stable? Least thermally stable. What according to you should be the answer? What according to you should be the answer? What according to you should be the answer? Least thermally stable, I am asking you. What I am asking you is least thermally stable. So you have a polyatomic anion, and in the case of the polyatomic anion, your stability depends inversely with the polarizing power of the cation. Okay, so if I ask you the polarizing power of the cation, you have Na positive ion and you have rubidium positive ion. Okay, both of them are considered as the same, which is the inert gas configuration. So how I will answer these two? Now I have to use simply the polarizing power of the cation. Smaller the size of the cation, greater is the polarizing power of the cation. Greater is the polarizing power of the cation. Greater is the polarizing power of the cation. Less is the thermal stability. So polarizing power of sodium positive is greater than rubidium positive. So the stability order, the thermal stability order will be greater for rubidium carbonate as compared to the sodium carbonate. Always first you have to follow this. Polarizing power of the sodium is ion is bigger and the thermal stability of the rubidium carbonate will be more. First we are moving towards this question. Next we have, let's say, beryllium carbonate and sodium carbonate. Okay, beryllium carbonate and the sodium carbonate. Now polarizing power of beryllium plus 2 is greater than sodium plus 1. If its polarizing power is greater, thermal stability will be less. Its thermal stability will be less. I hope this is clear to you. Thermal stability will be less. Now let's compare. Sodium carbonate and silver carbonate. Sodium carbonate and the silver carbonate. Now sodium positive is inert gas configuration. Ag positive is pseudo inert gas configuration, and which is having the greater polarizing power? You know that pseudo noble gas configuration is having greater polarizing power as compared to the inert gas configuration. So this is having the more polarizing power, so this will be more stable. Okay, so this sodium carbonate will have thermal stability more as compared to the silver carbonate, because the polarizing power of the silver positive ion will be greater. If you are having any confusion, I can let you see over here. This is pseudo noble gas configuration, this is inert gas or the noble gas configuration. It is having the more polarizing power, and thermal stability of anything which is having the polyatomic anion, its polarizing power of cation is greater, its thermal stability will be less. Its thermal stability will be less. So sodium carbonate will be thermally more stable, silver carbonate will be thermally less stable. Okay. Similarly, we can have a question over here. We have lithium hydroxide, we have sodium hydroxide, and we are moving towards the, let's say, cesium hydroxide. Now what is happening to top to bottom? See, all of them are of the inert gas configuration. So in the inert gas configuration, smaller the size of the cation. If I ask you top to bottom, polarizing power is decreasing. So thermal stability, the thermal stability will be increasing, and the same goes for the alkaline earth metal also, and same goes for the alkaline earth metal also. So I have discussed with you with the help of whatever is written in the last page. We have discussed all of the questions from that part. Okay, even you can have one more question, even you can have a one more question. Let's say I have calcium carbonate and I have cadmium carbonate. What will be the answer? Calcium carbonate and the cadmium carbonate. Calcium plus 2 is noble gas. Cadmium plus 2 is pseudo noble gas. So thermal stability, you know that polarizing power of the pseudo noble gas is greater. So thermal stability of calcium carbonate will be greater. Calcium carbonate will be greater as compared to the cadmium carbonate, as compared to the cadmium carbonate. If you have a greater polarizing power, your thermal stability will be less because you are having the polyatomic anion, you are having the polyatomic diatomic anion. Okay, I hope this is clear to everyone. I hope this is clear to everyone. Although I have written the question which is least thermally stable, but I have in all of the questions written the order of the thermal stability. I have written in all of the questions the order of the thermal stability. Now, let's discuss the next part, which is considered as the solubility. Next part which is considered over here is the solubility. 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 Next part we have to consider over here is the solubility. Now, how will you decide the solubility? Now, let's move from, let's say, any of the thing. Let's say we are moving from solubility. We have to discuss the order from top to bottom. Whenever in any group we are moving from top to bottom, whenever in any group, if we are moving from top to bottom, what is happening? When we are moving from top to bottom, always lattice enthalpy decreases, hydration enthalpy decreases, always. Okay, size of the ion is getting bigger, hydration will decrease. Okay, less energy will be required to break the molecule when it is having the bigger size. Okay, fine, no problem. Now, if, always remember, if decrease in lattice enthalpy is more, if decrease in lattice enthalpy is more, so decrease in hydration enthalpy will be less. Or you don't require to write this. Okay, just remember, in this case the solubility, in this case the solubility will increase, the solubility will increase. And if decrease in lattice enthalpy is less, in that case your solubility will decrease. First of all, you should know these two parameters through which your solubility will be decided. First of all, what they are saying, decrease in lattice enthalpy is more. You are moving from top to bottom, your lattice enthalpy value is getting decreased, but the decreasing value is very less. That means your respective lattice enthalpy is in such a way that the compound which is present at the last is requiring not very much high amount of energy to dissociate. It can dissociate it easily, so it will be more soluble. But if they are saying that decrease in lattice enthalpy is very less, that means it means that the top to bottom, your last compound, the last element compound, its lattice enthalpy is quite sufficient. It's not very easy to break that compound. In that case, the solubility will be less. Okay, you have to remember this thing. In nutshell, you can simply say, over here that the solubility will be increasing and the solubility will be decreasing. Now, let us move towards some of the compounds, how they are changing their solubilities, moving from top to bottom. First of all, we have a question over here. Lithium hydroxide, we have sodium hydroxide, we have rubidium hydroxide, we have cesium hydroxide. Okay, I'm just normally talking about the top to bottom behavior. So here in this case, when we are moving from top to bottom, our our decrease our decrease in lattice enthalpy is more. That means that hydration enthalpy, decrease in lattice enthalpy is more, decrease in lattice enthalpy is less. It means that your solubility when you are moving from top to bottom is increasing. Okay, decrease in lattice enthalpy is more, decrease in lattice and hydration enthalpy is very less. Okay, so the compound which is present at the very bottom is, it can be hydrated, and the compound which is present at the last can also be dissociated easily, so the solubility will be more. And same is the case for the alkaline earth metal hydroxide. Okay, same is the case. Even the similar case can be asked for these compounds also, which is lithium fluoride, we have sodium fluoride, we have potassium fluoride, we have cesium fluoride. When we are moving from top to bottom, here also the same case is there. Decrease in lattice enthalpy is more and decrease in hydration enthalpy is less. As a result, solubility will be increased when we are moving from top to bottom. And even remember that this respective lithium fluoride, the small ion, and the small ion have a very high lattice energy. They are having a stronger lattice. They are having a stronger lattice. It is hard to break. It is hard to break. That's why this respective compound is almost insoluble. It's almost insoluble due to very high lattice energy. Almost insoluble due to very high lattice energy. Small ion interaction, greater lattice, good packing, greater lattice enthalpy, almost insoluble. So all these trends are following the same concept I have explained. Now remember the other thing. Now what is happening is, let's say for the solubility I have the two cases. Always remember, whenever you are moving from top to bottom, whenever, these are the tricks you need to remember, whenever we are moving from top to bottom, if you are in the case of the polyatomic anion, okay, polyatomic anion if I am considering, polyatomic anion if I am considering, okay, in those cases, if the polyatomic anion is present, then number of anions is greater than number of cations. Number of anions is greater than number of cations. In that case, your solubility will be decreasing. Your solubility will be decreasing. But if you have number of cations more than number of anions, number of cations is greater than number of anions, in those cases solubility will increase. If the number of cations is more, solubility will be more. If your number of cations is less, your solubility will be less. Okay, now let us apply all of these concepts one by one. Let's say I have the sulfates of group 2. Okay, I have the sulfates of group 2. When I'm moving from top to bottom, what is happening? When I'm moving from top to bottom, the case over here is that number of anions is equal to number of cations. Okay, you have the same number of beryllium plus 2 is 1 cation, and sulfate over here is the anion. If you are taking whole as an anion, you will find it as equal 1. But here one thing more is present that you have to consider, that number of anions are actually greater than number of cations, because here you are only having the beryllium plus 2, here you are having S minus 2 and O minus 2. The number of anions are actually greater. So when number of anions are greater than number of cations, you are already writing over this thing. So you have to simply write over here that when you are moving from top to bottom, your solubility will surely decrease. Your solubility will surely be decreasing. And even you can write over here, the reason for this is barium is a bigger ion. Okay, it's combining with a sulfate, which is also a bigger ion. So big combines with a big to form a stronger lattice. To form a stronger lattice. So it's very hard to break that lattice. So it will be less soluble. It will be surely less soluble. But in terms of the reason, you have to write over here that beryllium sulfate and magnesium sulfate, they are highly soluble. You have to write this thing with a star, that they are considered that they are very highly soluble, because beryllium plus 2 and magnesium plus 2 have very high hydration energy. They have very high hydration energy. They actually have very high hydration energy, beryllium sulfate and the magnesium sulfate. Do remember this thing very, very nicely. Okay, very, very nicely. The solubility will decrease, and same will be the order for the alkaline earth metal sulfates. Same will be the order for the carbonate. Same will be the order for nitrates. Same will be the order for bromides. And same will be the order for the iodides. All of these ions will have the same order. All of these ions have the same order, whether you take the alkali metals or you take the alkaline earth metals. Okay, all of these have the similar kind of order when we are moving from top to bottom. Okay, but this is a very important question. This is sometimes asked very much. This is asked very much. Okay, you have to remember this thing. You have to write over here. You have to write over here. They have a stronger lattice. You have to write over here that hydration of barium plus 2. That hydration of barium plus 2 is very, very less because of its very greater, very bigger size. But you know, there are some exceptional orders also. There are some exceptional order also, and you have to remember those order. There are some exceptional orders also. What all orders are there? Now remember, if you have the group 1 chlorides, if you have the group 1 chlorides, so the order will be like this: lithium chloride, most soluble, then cesium chloride, then we have rubidium chloride, then we have potassium chloride, not potassium chloride, actually we have the sodium chloride, and then we have the potassium chloride. First of all, we have this exceptional order for the chlorides, and for the group 2, we have the exceptional order for the fluorides. These you need to remember. This is a experimental data. These you have to remember because this is a experimental data. And here it is having BeF2, then we have BaF2, then we have calcium F2, MgF2, and then BeF2. Okay, so this is all we need to understand. Okay, this is all we need to understand. This is all about the solubility of the compounds of the group 1 and the group 2 elements. Okay, I hope you people have understood. There are some exceptional trends, you need to learn them. There are some trends which are followed on some quick trick. You have to follow that trick. Always remember that trick. Tricks might because sometimes the order are exceptional. Okay, so let's move forward. Now let's discuss for the other compounds. Now let's say we have for the alkali metals, let's say we have for the alkali metals lithium sulfate, sodium sulfate, and till then we are moving towards cesium sulfate. In these cases, as you can know, that number of cations are greater than number of anions, right? You have two cesium positive ion, whereas you are having only one sulfate ion. So number of cations directly if you see is greater. So in this respective case, you can see that when you are moving from top to bottom, when you are moving from top to bottom, your solubility will increase. Your solubility will increase, and the same will be the order for the bicarbonates also. Like if you are moving from lithium hydrogen carbonate to, you are moving from lithium to cesium hydrogen carbonate, same is the case, your solubility will be increasing. Okay, so do remember, do remember the total order, what is happening top to bottom, what are the all important things associated with it, associated with it. Okay, so one thing I want to add over here, one thing I want to add over here is that that is the carbonates breakdown. Let's have the breakdown of compounds. Breakdown of the compounds. Let's have breakdown of the compounds. First of all, we have in the breakdown of compounds, let's say I have my carbonates. Let's say I have my carbonates. Let's say we have carbonates as the compound. Let's say we have carbonates as our compounds. So let's break any of the carbonate. If it is breaking into metal oxide plus CO2, okay, so metal over here will be lithium, magnesium, and all of the group 2 compounds. Okay, but this metal will not be sodium, potassium, rubidium, or cesium. Okay, similarly, if you break the metal hydrogen carbonate, okay, if you break the metal hydrogen carbonate, you are going to get the metal, you are going to get H2O, and you are going to get the CO2. Okay, you are going to get the metal oxide plus H2O plus CO2. Same is the case here also. Same is the case here also. Group 2 compounds will be breaking up like this. Group 1 lithium will be breaking up like this, but not with the case of the sodium, potassium, or the rubidium or the cesium. Okay. After that we have nitrates. After that we have the nitrates. We have to remember in the case of the nitrates also. Let's say I have a nitrate. It dissociates like this. It dissociates into oxide plus NO2 plus O2. In this case, M will be lithium and all group 2 elements. But if metal nitrate, dissociates to metal nitrite plus O2 gas, then that case metal will be sodium, potassium, rubidium, and cesium. So always remember what are all elements associated with it. What all the elements associated with this. Okay. You have to remember this. You have to remember this, that what all elements are associated with what breakage. Okay. I hope this is clear to everyone. Carbonates, nitrates. That's why sometimes it is called that lithium and magnesium. Lithium and magnesium do not form solid carbonates and bicarbonates. They have a diagonal relationship into this because when they form, they are easily broken up because that compound is not stable and it gets broken up into these respective compounds. Okay, so you have to remember the breakdown of the compounds also. Now, there is two words associated with molecules. One is called as hydration, not hydration, particularly we should say hydrolysis, and other is considered as dehydration. One is considered as hydrolysis while other is considered as dehydration. Dehydration and hydrolysis. Dehydration and hydrolysis. Now hydrolysis is something like if I take BeCl2 and I react that with water, what is going to happen? It will break into beryllium plus 2 and Cl negative. This will break into H positive and OH negative, and you are going to get beryllium hydroxide plus HCl. This is the reaction you are going to get. Okay, this is the product you are going to get. So this is hydrolysis. Okay, positive negative breakage and combining with the positive part with the negative part with the positive part. But if you have the dehydration, okay, let's say you have BeCl2 dot 2H2O. Let's say you have MgCl2. Let's take the very hydrated form, MgCl2 dot 2H2O. If you are undergoing the dehydration for this respective compound, so it will simply break into MgCl2 plus 8H2O. You will have this as your product. So there is a difference between hydrolysis and the dehydration, and you need to remember that. Okay. Now we are done with the important properties of the alkali metals, alkaline earth metals, which is the group 1 and the group 2. And now we have to discuss some important compounds of these respective group elements. Okay. So in this respective time, I have with my own hands, I have written everything. What all things were important are included in this lecture. You can rely on this lecture. Some of you, I have seen you people are writing that this lecture is enough or not, or all these things. See, everyone has a different aspect of if the lecture is lengthy, it's short, it's worth it, is it including everything. If somebody has studied nothing, he's having a different mindset. If somebody has studied everything, he has a different mindset. Okay, if you are seeing 100 of teachers, so you have a different mindset. If you are seeing a single teacher, you have a different mindset. So you yourself should watch the lecture, you should see the content, and then you should decide that is it applicable, it is appropriate according to your preparation or not. Okay, so let's start with the important compounds of the some important compounds of the respective group, which is group 1 and group 2. Now first of all, we have a very important compound of respective group 1 elements, and we will be discussing over here the compounds of the sodium and the calcium. Okay, calcium from group 2 and sodium from group 1. Mostly the questions from these two elements compounds are being asked. Okay, so we have the first compound over here, which is called as the sodium carbonate dot 10H2O. So we prepare this compound with the process called as the Solvay process. You have to remember whatever ma'am has written over here. Nothing extra you have to study, nothing less than this you have to study. Whatever is required, I totally made the notes for you. Okay. So Solvay process, first of all, what first question can be asked? What are the raw materials? So calcium carbonate, sodium chloride, ammonia and CO2 will be used as the raw materials. After that, you are going to mix first ammonia plus CO2 plus H2O. These all will combine to give you ammonium hydrogen carbonate. Now you are going to react this with NaCl. Okay. With NaCl, it is going to form sodium hydrogen carbonate as a precipitate and ammonium chloride, which will be present in the solution form. It is very important to add NaCl over here to separate these two respective compounds. One is your sodium hydrogen carbonate, which will be settled down as a PPT, and other will be the ammonium chloride, which will be present in the solution form. Now, sometimes a question can be asked that why I am using only NaCl over here, why I cannot use KCl over here? Because if you are using KCl over here, here you are going to get potassium hydrogen carbonate, and I have written the solubility order. Potassium hydrogen carbonate is having the greater solubility as compared to the sodium hydrogen carbonate. So these two will be very hard to separate. So that's why we never use here the KCl. Okay. After that, these compounds will be separated. Ammonium chloride will be reacted with the calcium hydroxide, because you are going to get this respective product, which will be the calcium chloride, and the sodium hydrogen carbonate will be heated to give you sodium carbonate plus water plus CO2. You are getting over here sodium carbonate, and then the water of crystallization will be attached when you react this again with the water. Okay, so this is how you are going to get the product. First, you should remember what all raw materials are there, what are the processes till this, what are the processes which are undergoing. After that, you are separating these two, and after separating, you are getting these two products. Okay, so this is how you are going to prepare sodium carbonate by the Solvay process. After that, we have NaOH. NaOH is prepared in a respective electrolytic cell, which is called as the Kastner-Kellner cell. I am writing all these things because these things are asked directly. The names can be asked directly. So Kastner-Kellner cell, electrolytic cell it is. After that, this is the industrial preparation method. Now, electrolysis of NaCl aqueous if we are performing. NaCl aqueous is also called as the brine. You know what is brine. But when we do this in the electrochemistry chapter, we were using the platinum electrodes. Here I am using the mercury electrode. Now, what mercury is doing? Okay. First of all, when you are performing the electrolysis of NaCl and the aqueous, which is the water, they will break like Na positive and Cl negative, and water will break like H positive and the OH negative. Now the Na positive and H positive will move towards the cathode, Cl negative and OH negative will move towards the anode. Now if the electrode is of the platinum, surely H positive will discharge and you are going to get hydrogen gas on the cathode. But when you are using mercury electrode is having a property that it decreases the discharge potential of the sodium positive ion. Sodium positive ion will be discharged first as compared to the H positive ion. Okay, at cathode you will get the sodium positive ion discharged first. You will get the sodium positive ion discharged first because mercury electrode decreases the discharge potential of sodium positive ion. Okay, and it will be formed as sodium Hg, because whenever there is a reactive electrode, it is seen in the form of the product. Okay, so sodium amalgam will be formed. Okay, at the anode, you know that the discharge potential of chloride ion is greater, but the oxidation potential of hydroxide ion will be greater. It is greater, but you know that in the case of the, for the discharge of the hydroxide, we have to supply over potential. So that is the case that it is not discharged. Cl negative is discharged prior to it. Okay, so we get a Cl2 gas. Okay, remember, if you dissolve this in the water, you're going to get ammonia, you're going to get sodium hydroxide plus H2 and plus mercury. Okay, this is simple extra question I have written over here. Okay, so this is all about the preparation of the preparation of the respective NaOH in the Kastner-Kellner cell. Remember one thing, here we cannot stop the reaction at sodium amalgam because we are discussing the preparation of ammonia. Okay, so you have to dissolve the sodium amalgam into the sodium in the water to get the sodium hydroxide. Done. After that, we have over here the calcium oxide. Calcium oxide having a different name, which is known as the quicklime. You dissociate calcium carbonate, you get calcium oxide plus CO2. You dissolve calcium oxide into the water, you get calcium hydroxide. It is also called as slake lime. Okay, it is also called as the milk of the lime. Okay, sometimes there is a difference of that milk of lime and the lime water. When it is present as the precipitate, it is called as the milk of lime. When it is present in the solution form, it is called as the lime water. Okay, both are having the same formula. There is no difference in the formula. So you have to remember this. Okay, now we have next compound, which is the slate lime. So calcium oxide, when reacts with water, you get the calcium hydroxide. When it reacts with CO2, you get the calcium carbonate. So calcium hydroxide is considered as the slate lime. Further, its process with CO2 gives you calcium carbonate, and further if you supply CO2 again and again, you are going to get when you again supply the CO2, excess of CO2, you are again going to get the calcium hydrogen carbonate. Okay, here you have a milkiness appeared because of the presence of the calcium carbonate, but if you supply large amount of the CO2, your milkiness will disappear. Okay, so you will be having the calcium hydrogen carbonate as no milkiness. Okay, so these are the two next important compounds which are for the calcium. After that, we have calcium sulfate. For the calcium sulfate, first we have the preparation. Calcium chloride reacts with H2SO4 to give you calcium sulfate. Now, first we are having the gypsum part, which is twice of calcium dot 2 H2O. Okay, if you will divide whole by 2, you will get the different formula. Okay, so this is called as the gypsum. Gypsum is something which is having the hardness also, which is having the strength also. Okay, like we have a plaster of Paris. Okay, if you heat this with the 120 degrees Celsius temperature, you are going to get the plaster of Paris. Whenever we have a fracture, we have a plaster over here. It is very hard, but it's not having very much strength. If you'll have a pressure to it, it will break very easily. So gypsum is something which is having the strength also, which is having the hardness also. Okay, so if you apply 120 degrees Celsius temperature to gypsum, it is converted into the plaster of Paris, which is having this respective formula. If you heat it again, you are going to get the dead burnt plaster. All of these three names are being asked in the JEE Mains examination so many times. And further, if you are heating it, you are going to get calcium oxide plus SO3. Okay, so these are the names you need to remember. These are the composition you need to remember. Very, very important. Okay, after that, we have the cement. Now we have the cement. Okay, in terms of the cement, first you have what all components are present. Okay, calcium oxide, silicon oxide, aluminium oxide. So many compounds are present over here. So many compounds are present over here. And what are the percentages present is also written for you. So this is something which is the learning part. You have to learn this respective box. After that, whenever you are going to make the Portland cement, what are the raw materials for that? First, you have to take the clay. Now, clay is the mixture of silicon oxide, aluminium oxide, and the iron oxide. All these three combines to give you the clay. After that, lime and clay are mixed. Lime is calcium oxide. They mix with each other to give you a compound which is called as the cement. Okay. When we add these two things along with the cement, we are adding over here a compound which is gypsum also. Now, the question can be asked, like, lime and clay are mixed to give you cement. Now, you are mixing gypsum into it. What is the need to mix the gypsum into it? So, you should know the basic functioning, basic role of the gypsum over here. First of all, it increases the polymerization. Okay, since you are adding the gypsum in this respective cement, it makes the product as a polymer. When there is a polymerization in a product, there is an extensive network linkages everywhere that provides solidity to it, that provides strengthening to it, hardness to it. Okay, so when you are adding gypsum, there is a polymerization and to increase the setting time. Okay, you are adding gypsum into it in the cement, you are adding water. Whenever you have your home's construction, okay, you put a cement, then every of the evening you are putting water, because when you apply water to it, you are actually making it more strengthening. Okay, so you are getting the Portland cement. Now, Portland cement is also having all these things present with it: calcium silicate, dicalcium silicate, tricalcium silicate, and tricalcium aluminate. With all of the percentages I have written: 26%, 51%, and the 11%. Question has come in the JEE Mains 2021. In this, from this portion, I have made 3 stars over here to understand that this is something important. So this is all about the cement, how Portland cement is made, what is clay, what do you mix in the cement to increase the polymerization, to increase the hardness, okay, and what are the composition of the these all compounds present in the cement. So this is something very, very important portion. These all compounds you need to remember very, very nicely, okay. Now we are going to discuss the important questions of the S block elements. Now let's discuss about the questions of the S block elements. So the first question we have over here is the radioactive element present in the first group of the S block elements, right? So if you want to know about the radioactive elements, so in the first group we have lithium, sodium, potassium, rubidium, cesium and francium. These all are the elements which is present in the group 1 of the S block element, in which this francium is considered as the radioactive element. So the answer will be francium, right? Moving towards the next question. The least electropositive alkali metal. You have lithium, sodium, potassium, rubidium, cesium and francium. We have all of our elements like this. When we are moving from top to bottom, our electropositive character increases. So this will have the least electropositive character, and we don't consider radioactive elements in most of our considerations. So we will take cesium. We don't study much about the radioactive elements because they are very hard to handle. So the least electropositive element will be considered over here as lithium, because when you are moving from top to bottom, your electropositive character increases. So the first one will have the least electropositive character. The flame test which is given by the sodium, you know that during the flame test we have lithium, sodium, potassium, rubidium, cesium. I have given you the trick to learn all these colors, okay. So I have written CYVRB. I have explained you these tricks in the notes, so you can follow for the sodium as yellow. So just find the yellow over here, which is the golden yellow color, right? The alkali metal atom that easily forms the cation, no problem. So if you want to form the cation, let's say you are an element, you want to form the cation, so you will ionize yourself, है ना? I should first convert it into the gaseous form. After that, this M gaseous will ionize. It will ionize to give you one electron. Right? So for removal of the electron, you are requiring the energy over here. Which is called as the ionization energy. So you have to just check the ionization energy in this respective question. The alkali metal that can easily form the cation, which can easily release the electron, which have the least ionization energy over here. The order of the ionization energy you can write over here. The order of the ionization energy will be lithium, sodium, potassium, rubidium and cesium. This is the order of the ionization enthalpy. So the answer will be cesium, right? Let's move forward. Which one of the following has a polarizing power close to that of the magnesium? Now, whenever you want to calculate the polarizing power, this is also the question from the chemical bonding. Whenever you want to calculate the polarizing power, always remember it is directly proportional or it is equal to charge by radius ratio. It is directly proportional or it is equal to charge by radius ratio. And lithium, sodium, beryllium, magnesium, these two elements have a diagonal relationship. These two elements have a diagonal relationship. They have a diagonal relationship because they have similar polarizing power. They have similar polarizing powers. So lithium and magnesium will have the similar polarizing powers, right? So this is how you have to solve this respective question. Now moving towards the next, beryllium chloride can be prepared by passing the chlorine vapors over the heated mixture of. See, the problem is whenever we are making the beryllium halides, right? Whenever we are about to make any of the beryllium halide, it's not easy to make them directly. We cannot just react the beryllium with the halogen and we will get the beryllium halide. That is not possible because beryllium is having a very high amount of the ionization energy. So we have to use some indirect methods for the preparation of the beryllium halides. Okay, direct preparation is not possible. Direct preparation is not possible. So I am making a cross over here. We cannot have a direct preparation for the beryllium halide. So what we do, we take beryllium oxide, okay, and we react this with carbon. Okay, after that we have Be, chlorine vapors. Okay, we have to take the chlorine vapors also. So we will take the chlorine vapors also over here. Then we will be able to make BeCl2 plus carbon monoxide. So this is the reaction you are going to get in this respective question. So we have to take care that which of the beryllium halide we have to prepare. It is Cl2 vapor. So just put the Cl2 vapors on the conditions. Okay. Next we have over here dead burnt plaster. Nothing. Dead burnt plaster is something which is not having any water of crystallization. There will be no water of crystallization. There will be no water of crystallization in the dead burnt plaster. So the answer will be option number D. Okay. Moving towards the next, the most abundant metal present in the human body. So you have to check over here the most abundant element, which is, it's just a learning part because we have to see this for the NCERT, the uses of the alkali metals and alkaline earth metal which is present in the NCERT. From there you can find out the most abundant element or the metal present, right? Next we have the solubility in water is more for. Here we are having the carbonates and the carbonates of the alkaline earth metals we have. We have over here the carbonates. We have over here the carbonates of alkaline earth metals. We have the carbonates of alkaline earth metals, and when we move from the beryllium carbonate to barium carbonate, when we move, the solubility will decrease. The solubility will decrease because this is a bigger ion. Barium is also a bigger ion. Bigger ion and bigger ion will have a stronger bond. This beryllium is a very small ion. Carbonate is a big ion. The smaller and the bigger ion will not have a stronger bond. So these two will have a greater lattice energy. Okay, so the breakage of this respective compound is hard, so its hydration energy will be less. This will break very easily because the bond is not stronger. One is small, one is weak, so it will be easily broken up, so it can be hydrated easily. So the solubility in water is more for, it is more for the beryllium carbonate, right? Just remember, solubility will decrease when we are moving from top to bottom. Which of the following is the most basic? The more basic or the most basic? No problem. We have over here beryllium hydroxide, then we have magnesium, then we have calcium, then we have strontium, and then we have barium and the barium hydroxide. So when you are moving from top to bottom, your basic character increases. So barium hydroxide, the barium hydroxide will be considered as will be considered as most basic. It will be considered as most basic barium. Next we have, which of the following is different from the other three oxides? First we have magnesium oxide, tin oxide, zinc oxide and the lead oxide. There is no issues in this respective question. You have to check over here first of all the amphoteric oxides. You have to first check the amphoteric oxides. And in the case of the amphoteric oxides, we have zinc oxide, we have beryllium oxide, we have aluminium, we have lead, we have tin, and we have arsenic, in which we have the lower oxidation state. Even we have the As2O5, but that is not the amphoteric oxide. Only the As2O3 is amphoteric. Zinc oxide, beryllium oxide, aluminium oxide, PbO2, SnO2, right? We have Cr2O3. All these elements are having the amphoteric oxides. Now, which one of the following is different from the other three? This is amphoteric, this is amphoteric, and this is amphoteric. All of these are amphoteric. All of these are considered as amphoteric. You can add over here this also, lead oxide, tin oxide. Okay. So all of these are amphoteric, only this is different. So this will be the answer. Okay. Magnesium oxide is the basic oxide. Magnesium oxide is a basic oxide. It's a basic oxide. Next have hardest alkali metal. When we are moving from lithium to cesium, when we are moving from lithium to cesium, this is considered as the most hard. When you are moving from top to bottom, your hardness will decrease. So this is considered as the most hard. The lithium is considered as the most hard. The highly reactive alkali metals are kept in. See, there is a problem with alkali metals. Alkali metal can react with the moisture very easily. Okay, so they are kept in the kerosene. Lithium is not able to, we cannot keep lithium in the kerosene. The problem is because lithium is having a very less density, so it floats on the surface. So that's why we keep lithium in the wax, the paraffin wax. Okay, but here they are simply asking you the highly reactive alkali metals, because they are easily reacting. So they should have a barrier on themselves, so they should not come in contact with anything with which they can highly react with. Okay, so they are kept in the kerosene. Okay, all alkali metals mostly are kept in kerosene. Lithium having low density kept in paraffin wax. Kept in the paraffin wax. Okay, beta. So remember this. Next we have the alkali metal that is soluble in the pyridine. Now you have to first keep in your mind about the pyridine. Now this respective pyridine is an organic solvent. Which dissolves covalent compounds. Mostly it dissolves the covalent compounds in itself. It dissolves the covalent compounds in itself. Now what happens is, you have to find in all these four options which is the most covalent. So for the covalent character, you have to see the Fajan's rule. For the covalent character, you have to see the Fajan's rule, which is, in this case we will take smaller size of cation, bigger size of anion, greater is the covalent character. Even in the notes also we have discussed about this. So here chloride is same in all of them. So we have to just see the cation. Sodium, lithium and potassium. Which is having the smallest size? Lithium. So the smaller the size of the cation, greater is the covalent character. Greater is the covalent character, greater it is soluble in the organic solvent. So lithium chloride will be soluble in the organic solvent. Now some of them will think, ma'am, cesium iodide you have not taken, because in this case iodine is present. Iodine is having a very large size. So greater the size of the anion, greater is the covalent character. Okay, here also we are having the greater covalent character. But in the case of the cesium and lithium, lithium is having a very small size, very small size. That's why its covalent character will be more. So that's why your answer will be option number B. Among the following, the least thermally stable, the least thermally, always you have to look for this option, because it is, I have written this thing in the exceptional behavior also, in the anomaly also, in the diagonal relationship also. I think so many times I have written in the notes that lithium carbonate is considered as the most unstable carbonate of the alkali metal. It is considered as most unstable, it is considered as the most unstable carbonate of alkali metals. It's the most unstable carbonate of the alkali metal. So you have to remember this thing very nicely. It dissociates to give you lithium oxide and the CO2 gas, right? For alkali metals, which one of the following trends is incorrect? Hydration energy. The trend of the hydration energy is completely correct. There is no problem in the trend of the hydration energy, because you know that hydration energy is directly proportional to the charge by radius ratio. So charge is same in everyone, but the radius, which one will have the smallest radius, will have the greater hydration energy, because they are having the inverse relationship. If you have the greater hydration energy, that means you have a very small size. That means you have a very small size. That's why the order is like this, and that is the correct order. Ionization energy. You know that ionization energy is also inversely proportional to the size. So if you have a bigger size, your ionization energy will be very less. So this is also correct order. This is also correct order. Density. Now density is having some problem. The correct order of the density is not like this. It is lithium, and then we have potassium, then we have sodium, and then we have rubidium. This is the correct order of the density. There is an exception in the case of the potassium and the sodium, so that you have to remember. So this order is incorrect. Now we have atomic size. Yes, when we are moving from top to bottom, size increases. When we are moving from top to bottom, size increases. So the size order is also correct. So which order is incorrect? So answer will be option number C, that is the density one. All of these things are present in your notes. If you have seen the notes, you will be easily able to answer this question, right? Next we have the characteristics not related to the alkali metals. Okay, their ions are isoelectronic with the noble gases. Their ions. Let's say I have a lithium, I have sodium. Lithium is having electronic configuration 1s2, 2s1. This is having 1s2, 2s2, 2p6 and then 3s1. Now I make the ions of these two. Now what I do? I will make the ions of these two. So lithium positive I will make, which will have the electronic configuration as 1s2, and the sodium positive I will take, which will have 1s2, 2s2, 2p6. Now keep this thing in your mind. That what are the electronic configurations of the elements you are getting as a result. This is lithium positive as helium, and this is neon. So their ions are equivalent to the electronic configuration of the noble gases. So this statement is correct. They have a low melting point. Not related to. They have a low melting point. That is correct. Low electronegativity. When we are moving from left to right, yes, electronegativity increases. So they are highly electropositive. They should not be having the electronegativity. Actually, they have a very high electropositive character. They have a very high electropositive character. So this is also correct. This is also correct. They have a very high ionization energy. I should not say that they should have a very high ionization energy, because the reason is they have a bigger size. They have a bigger size. They are talking about the alkali metals as a whole. So we should not take the ionization energy as top to bottom. Alkali metal as a whole will be compared with all of the other groups, the 2nd to 18th group. So alkali metals is present in the group 1. After that you have your respective group number 18. So this respective group is of the alkali metals. This respective group is of the alkali metals, which is having the very large size. And when we are moving from left to right, size decreases, ionization enthalpy increases. So how can you say that alkali metals is having the very high ionization energy? Okay, so they have a very big size, that's why they have a low melting point. Okay, here the size is not calculated on the basis of the van der Waals forces. It is calculated on the basis of the metal forces. As the size increases, the metal bond increases, their melting points become lower. So that's why this point is also correct. They have low electronegativity because they are highly electropositive. This is also correct. So only the option which is not we are finding correct is the high ionization energy. Alkali metals are good reducing agents because, first of all, you should know that what is a reducing agent. Whenever we have to talk about the reducing agent, what things should come in our mind? In the case of the reducing agent, if you want to discuss about the reducing agent is someone which reduces someone else and oxidizes itself, है ना? So it will oxidize itself to release an electron. So everything is based on the ionization energy, right? We have to talk about the ionization energy. So greater is the ionization energy, okay, less is the ability of becoming the reducing agent. We should not write this much. It's not required to write this much. Just have one thing in your mind: if you have a greater ionization energy, you will be poor reducing agent. So just have an order of the, even they are not asking you the order also. The question is already very easy. I don't have to even write the order. They are simply asking because they lose electrons, nothing else. Nothing else they are asking. Just lose electrons, reduce someone else, oxidize yourself. Whenever you are losing electron, whenever you are losing electrons, you are getting oxidizing self. Oxidizing self. Which one of the following metal carbonate is decomposed on heating? So always remember, lithium carbonate and magnesium carbonate. Always remember that lithium carbonate and magnesium carbonate, they are thermally unstable. They are thermally unstable and they can easily break. They are thermally unstable. They can easily dissociate. So the answer will be option number A, which is magnesium carbonate. Okay. So I have written these things in the notes itself. Okay. So nothing is there that you are not knowing. This is present in the notes. You can simply see and you can answer the question. Lowest melting point chloride among the following. Okay. Now, if you want to discuss about the lowest melting point, so I should tell you one thing first, that your melting point here is directly proportional to the ionic character. Greater is your ionic character, greater is your melting point. Greater is the ionic character, greater is your melting point. Now you have to calculate the ionic character. Now for the ionic character, for the ionic character, you should have a big size of cation, you should have a small size of anion. Big size of cation or the small size of the anion. So halides anion is same. What you have to see? You should have a big size of the cation. So big size of the cation is for the cesium. So cesium over here will have the highest melting point. And what they are asking you is the lowest one. So lithium will have the lowest melting point. This is the theory you have to use in this respective question. I hope this is clear to everyone. Let's move forward. Which one of the following alkali metals gives hydrated salts? Okay. Alkali metals and the hydrated salts. There is no problem in this question. We know that hydration depends upon the charge by radius ratio. I have explained about the hydration so deeply in the chemical bonding lecture. Some of you are not knowing anything about hydration. If you are not looking at the lecture of the chemical bonding, then some of the things are very hard to understand. Okay, that is a one shot lecture. That is not the very detailed lecture, because detailed lecture will require at least 15 to 16 classes. That is the minimum I can say. So it's a one shot lecture. So whatever you can get from that lecture, please take it and write it in your notes, because whatever I'm explaining you right now will be required in that lecture. Okay. Now hydration is equal to charge by radius ratio. Okay. So lithium is highly hydrated. Lithium is highly hydrated. Why? Because if I compare the charge by radius ratio of lithium, sodium and potassium and cesium. Lithium, sodium, potassium and cesium. So everyone is having the positive 1 charge, and the size over here is like this: 1, 2, 3 and 4. So the greater the size you have, less is the charge by radius ratio you have. So lithium over here is highly hydrated. It is highly hydrated. The lithium over here is highly hydrated. It is very highly hydrated. That's why its salts are also hydrated. We have the lithium salt as LiCl dot 2H2O. Lithium is having 2 water of crystallization. So which one of the following is highly hydrated? So lithium is highly hydrated. 4 alkali metals. Now we have 4 alkali metals A, B, C and D, and they have the standard electrode potentials. Now some of you are not knowing what is electrode potential. Now this is something which is explained in the class 12th, but whatever I'm explaining you, just try to understand if you can understand, because this is not something very difficult, but if you will listen carefully, you will get to know what is happening in this respective question. Okay, so whenever they are asking you the standard electrode, whenever they are talking about the standard electrode potential, whenever they are talking you about the standard electrode potential, that means they are talking you about the M plus N upon M. Now what is this? This is something that Mn plus is getting converted into M, and for that whatever potential is required is known as the reduction potential. Because obviously, like let's say I have M plus 2 as the oxidation state and I'm becoming M, so I'm reducing myself in this case. So this is simply the reduction potential. This is simply the reduction potential. This is simply the reduction potential they are talking about. Okay, first of all you should know the what they are saying. So they are saying that the reduction potential order of some of the elements, which is written over here, A, B, C and D. The reduction potential of some of the elements is written over here for the A, B, C and D. For the A it is written as minus 3.05. For the B it is written as minus 1.65. For the C, it is written as 0.40, and for this, it is written as 0.80. That means they are saying that when A is reduced, it is getting whatever potential it is requiring for that conversion is minus 3.05. Okay. Now, which will be the most better, or which is the best reducing agent? Reducing agent is that you have to undergo the self-oxidation. Now, this is written as the reduction potential. Okay. So, there is a relationship between, now this is the reduction potential, and the oxidation potential is always the opposite of that. Okay. Always remember, there is a relationship between reduction potential and the oxidation potential. So they are always opposite of that. Let's say I am having, for an example, I have an element, let's say I have A. So A, in this case, they are telling you about all of these other reduction potential. That means when A positive accepts at electron and becomes A, its potential, the reduction potential which will be required is minus 3.04. When A is getting reduced, what is the potential you are requiring? Minus 3.04. Let's say if A is getting oxidized, so its oxidation potential now will be plus 3.04. Now it will not be the negative one, now it will be the plus 3.04. Okay, first it was negative, now it's positive. Plus 3.04 will be the potential. Okay, now you have to compare the ability of the being reducing agent. That means you have to self oxidize yourself. So better is the ability to oxidize yourself, or better is your oxidation potential, greater will be the strength of being as reducing agent. So if these are the reduction potentials, make the oxidation potentials 1.65 minus 0.40 minus 0.80. So in the first table, this is having the highest reduction potential. So it is having the highest ability to reduce. It is having the highest oxidation potential. So it is having the highest ability to oxidize. It is having the highest ability to oxidize itself. That means A is having the highest ability to oxidize itself. That means A is the best reducing agent. For being reducing agent, you must have the strongest power to oxidize yourself. If these are the reducing agents which will be having the highest if these are the reduction potentials, so which one is having the highest reduction potential will have the highest ability to get reduced. Calculate the oxidation potentials, just make the signs as opposite. This is having the highest oxidation potential, highest ability to oxidize itself, so it will be the best reducing agent. So this is a theory which is required. Okay, at this point of time we tell students to learn, but I don't think so that this is something very hard that you will not be able to understand. If you listen to me carefully, you can get all of these values. You people are in 11th standard and you should know all these things. You are the victory batch students, you should know all these things. Okay, let's move forward, guys. The elements that reacts with the cold water, this is also present in the notes. Okay, always remember that beryllium does not react, or if you want to react beryllium, it's very hard for beryllium to react with water. It's very hard for the beryllium to react with water. Okay, sometimes they say that it does not react even. They say that it does not react. Magnesium reacts with the hot water, and after that your calcium reacts with the cold water, and all of the other elements, they also react with the cold water. Okay, so cold water is for the calcium. Answer option number B. Beryllium does not react. Top to bottom, the reactivity with the water increases. Okay, so if you want to react the above elements with water, you have to give the temperature to them to initiate the reaction. So that's why we use the water as the hot one. top to bottom, the reactivity is normal, it is increasing, so you do not require any temperature for the reaction to occur, so you can react with the cold water also. Okay, the ionic mobility of the alkali metal ions in the aqueous solution, the ionic mobility, this is also I have explained so nicely in the so deep in the chemical bonding. Please watch the ionic bonding. There I have explained you solubility, hydration, polarizing power, how hydration, ionic mobility, all of these things are connected. Even this is also asked if you are giving any examination right now, JEE means, or I have given the lecture before the NEET examination, because my point of view was that if anybody is giving the examination, if they are looking at that lecture, they will have a very good amount of the help in understanding what is important with respect to examination. Whatever is present in the lecture is the most important topics. I have given the very short theories because I was limited with the time, because I had to give the one short lecture, the 15 lectures chapter in the one lecture. So I have covered all of the important topics. You should watch all of them, because right now whatever theory is required is present in the chemical bonding. Now, understand that whenever we are talking about the hydration, whenever we are talking about the hydration, that is directly proportional to the charge by radius ratio. Hydration is directly proportional to the charge by radius ratio, and greater is the hydration, less is the ionic mobility. Greater is the hydration, less is the ionic mobility. Greater is the hydration, less is the ionic mobility. Okay. So the order of the hydration, just see that all of the elements are having the smaller size, not the smaller size, all of them have the similar charge. So just see the radius, greater the radius, less is the hydration. Okay, so the hydration order will be lithium highest, then we have sodium, then we have potassium, and then we have rubidium. So this is the order of the hydration we have. So we can simply write over here, it is having the least ionic mobility, and this is having the highest ionic mobility, and whole concept is explained in chemical bonding chapter. So nicely, so deeply I have explained you, so nicely, so deeply I have explained you. Please go to that lecture of chemical bonding, ionic bonding, solubility of ionic compounds. There I have explained this very nicely. Now NaOH is prepared by which method? NaOH is prepared by the electrolysis of NaCl aqueous, which is the brine. Okay, we get over here Na positive plus Cl negative, we get over here H positive and OH negative, because you know that if we have the NaCl aqueous solution, we have the water also present with us, so it will also dissociate, and you have to use the mercury electrode. Using the mercury electrode. Okay, so this is in the Kastner-Kellner cell. There is a name of the cell, electrolytic cell. Like in the case of the zinc and copper, we name the electrolytic cell as the Daniell cell. So in the case of the sodium preparation, it is called as the Kastner-Kellner cell. That's it. Okay, so these two ions are moving towards the cathode, because cathode over here is negatively charged, and these two ions are moving towards the anode, which is positively charged. So here we get the sodium, which is taking one electron and it is forming the sodium, and sodium reacts with the mercury because there is a mercury electrode, and it is deposited as NaHg, amalgam of sodium. Okay. In the case of the anode, there is a chloride ion moving and hydroxide ion moving. Here the chloride ion is discharged, but they are simply talking about the preparation of NaOH that we have to consider. So this is done with the help of the Kastner-Kellner cell. This sodium amalgam you can break, It is giving you Na positive ion, and from here you are taking the OH negative ion. Cl negative will be discharged to give you the Cl2 gas. OH negative from here, Na positive from here, they combine to give you the NaOH solution. That's it. Okay, this is how you have to prepare, and this is also I have discussed in the notes. You can see from the notes also. Next we have over here molecular formula of the globular salt. This is something you have to remember, that the globular salt is Na2SO4.10H. That is a decahydrate of the sodium sulfate. The final product in the Solvay process. So what do you get in the Solvay's process? It is used in the preparation of the sodium carbonate. It is used in the preparation of the sodium carbonate. It is used in the preparation of the sodium carbonate, that is dot 10H2O. And what are the raw materials used in the Solvay's process? Whole of the process I have explained in the notes in the case of the Solvay's process. So whatever are the initial ingredients you have to use, you have to remember all of these. Whole of the process is explained in the notes. You can refer that. Next we have, when sodium metal reacts with acetylene, the product formed is. Now this is the reaction which will come in the organic chemistry. So understand that when sodium reacts with acetylene, what happens? I don't know if you are a 11th class student, very small student, 11th class. So some of the things you are not knowing for the organic chemistry. So you might sometimes find this hard. It's not hard. It's because you have not studied the organic chemistry. So some of the concepts are not familiar to you. It's not hard, beta. Whatever I teach in the class is never hard. The thing is, some of the things are coming in the further chapters, so you are not aware of them. So just learn some at this respective time that what is happening, and when it will be explained in the respective chapter, the deeply, the thoroughly, you will be able to get the content more effectively, right? So what is happening now? What happens now? This respective sodium first convert itself into sodium gaseous. Now there will be release of the electron from the sodium. There will be release of the electron from the sodium, Na positive plus electron, and this will be dissociated as C negative, and we will get the 2H positive ions. We will get the 2H positive ions. Now what happens? This is the compound, and one sodium positive is attached over here and other sodium positive is attached over here. So first product you're getting will be this. I'm just attaching the negative part with the positive part, nothing else I'm doing, okay? After that you have the 2H positive and you have 2 electrons with this, okay? Because I'm taking only one sodium over here, but it is having Na solid, so you're having n number of sodium present in this respective piece of the sodium, okay? So H positive will accept an electron to form H, okay? One H combines with the other H to form the hydrogen gas. So you will get along with this the hydrogen gas. So this is the product you're getting, Na2C2. Okay guys, I think you people have understood. You people are very intelligent. You can go very parallel with me. I know you people can catch things even it is not taught to you in any of the class, है ना? The decreasing order of the hydration enthalpies of the group. Second, hydration enthalpies is so important. You can see from here in so many examination lists coming. These all are the PYQs present in your class today. So I think from the 10 question, if I can say 5 questions are coming from the hydration. So you can understand that the hydration concept is so important and you have to study that from the chemical bonding chapter, and you are promising me that yes ma'am, we will study. Okay. So no problem, top to bottom, again I am writing, again I have to write that hydration is directly proportional to charge by radius ratio. Everybody is having the same charge over here, so we have to discuss on the basis of the radius. Smaller radius, greater hydration. So size order you can simply see: beryllium, calcium, no, beryllium, magnesium, calcium, strontium, barium. Option number D will be the answer. Simple. Epsom salt, this is also something you have to remember. It's just a name. Sometimes it's asked what is an Epsom salt, so you have to remember MgSO4.7H2O. Which of the following elements does not form hydride by direct heating? Always remember, there is a problem with beryllium. There is always a problem with beryllium. That's why it is even not considered as alkaline earth metal, because always it is having problem with this thing or that thing. Now he will not be forming the hydride directly. Now we have to make an indirect method for the preparation of the hydride of the beryllium. Beryllium hydride cannot be prepared directly. So if you are thinking that you react beryllium with the hydrogen and you are forming the BeH2, this is not possible. This reaction is not possible because it does not form the hydride directly. Okay, so the answer will be option number A. Which of the following is used in the cancer radiotherapy? Now these are the uses: beryllium, strontium, radium, and none of these. So radium is used for this respective purpose. For this you have to go for the NCERT uses. From there you will be easily able to find out this respective question. This metal is used to scan the X-rays of the human digestive system. Bicarbonate, sulfates, barium and magnesium. So barium is used for this respective method. This is also uses beta. This is also something you have to learn. In which of the following the hydration energy is higher than the lattice energy? Okay, now they are asking you about the sulfates. Even this question is very important with respect to the examination points of view. For the solubility of the alkaline earth metal sulfates, question is asked. Many times it is asked. Okay, so we have beryllium sulfate, magnesium sulfate, and moving towards the barium sulfate. So when you are moving from top to bottom, hydration enthalpy decreases. Okay, this respective beryllium plus 2 and this respective magnesium plus 2, due to the small size, they are highly hydrated. Due to the small size, they are very highly hydrated. Due to the small size, they are very highly hydrated. So, in which of the following hydration energy is higher than the lattice energy? Because in the case of the barium sulfate, both of the ions are big. This is also a big ion, this is also a big ion. So, big and big ion is having the greater lattice enthalpy. So, it's hard to break the bond. In the case of the beryllium sulfate, one is small, one is big. So, you can easily break the bond of the beryllium sulfate. So, if you can easily break the bond, beryllium you will get, sulfate you will get, beryllium will be very highly hydrated because of its very smaller size. So, answer will be beryllium and magnesium. So, beryllium is not present over here. So, you will write the magnesium sulfate. No beryllium is present, so magnesium sulfate you have to take. Hydration energy is greater than lattice energy. That means if you break the compound, you will require some of the energy. But when it is broken up and it is dissolved in water, it is a very high amount of energy is released for the magnesium and for the beryllium. That is the question present in front of you. Okay. Aqueous barium hydroxide, it's known as baryta water. That is something you have to learn. Baryta water. Which of the following sulfates has hydration energy higher than the lattice enthalpy? Same is the question I have discussed right now. Beryllium and magnesium, same question. All of the questions are from the PYQ. All of the questions are from the PYQ. Which of the following metals cannot give the flame test? You know that from the alkaline earth metals. You know that in the alkaline earth metals, beryllium and magnesium. You know that from the alkaline earth metals, beryllium and magnesium do not give flame test due to high ionization energy. It's very hard to excite the electron of these two elements to the higher state, so that's why they do not give any kind of the color. Beryllium and magnesium both, they do not give any color. Rest all of the elements of the alkali metals give color, and the alkaline earth metal also. Sirf beryllium and magnesium will not give the color. That is also we have discussed in the notes. The iron helpful for controlling heartbeat and the muscle contraction. That is uses calcium. You have to go for the uses from the NCERT. KO2 is used in the oxygen cylinders in space and submarines. This is also a very important application of the potassium peroxide. You know, it is used in the submarines. It is used in the submarines. What happens? It absorbs the CO2 from the submarines to form the carbonate, and this CO2 is converted into the oxygen gas. So it's a very useful compound in the case of the environment, in the case of the submarines, whatever you want to say. So it absorbs CO2 and it increases O2, right? It's very, very important. It's very, very important. It's asked, I think, so many times this question has been uh, calculated. Amphoteric hydroxides react with both alkalis and acids. That is the definition of the amphoteric oxide, that it can react with the acids also, it can react with the bases also, right? Now, which of the following group 2 metal hydroxide is soluble in the sodium hydroxide? Now understand that the alkaline earth metals is having alkaline earth metals, that is beryllium, magnesium, calcium, strontium and barium. Okay, we have all of these elements present with us. Now, this is not considered as alkaline earth metal, whereas all of these are considered as alkaline earth metal. Okay, and they all form the basic oxides. So the basic oxides are not soluble in the bases. Okay, the amphoteric oxide is soluble in the bases or the acids. They will react with the acid, they will not react with the base. Okay, so you have to understand what is the concept. Which one of the following metal hydroxide is soluble in the sodium hydroxide? Okay, it can react with the acid also, it can react with the base also, but all of these are the basic oxides. They will not be soluble in the base. Understand? Okay, so the option will be answer number A. When sodium is dissolved in liquid ammonia, a solution of a deep blue color is obtained. We know the reaction. We know that reaction, that whenever the sodium or any metal, I should not say sodium, any metal, when it is dissolved in the ammonia, when it is dissolved in the liquid ammonia, I have explained this reaction very nicely in the notes also. You get ammoniated metal, you get the ammoniated metal plus ammoniated electrons. Ammoniated metal and ammoniated electrons. Okay, and this respective solution is having the color, as blue, and which is due to the ammoniated electrons, I have explained this thing in the notes also. You can refer from that, and if you want to know the answer, I have written on the blackboard. Ammoniated electron, whenever you want to see the electron, that is always due to the whenever you want to see the color, that is always due to the electrons, and that should be an unpaired electron if you are going more in the deeper manner. But that right now you can simply just say that it is ammoniated electron. Obviously metal is not responsible for the color. Color is first of all responsible because of the electron. Electron is gaining some energy, it is going towards upper level, then coming to the lower level and giving some of the radiation which is contrary to what it has absorbed, that we study in the physics. Even in the structure of atom, ma'am has explained you that absorption spectrum, emission spectrum, from that you can see the color phenomena. Okay, so the answer number A is the option, and here we are completing the S block elements. See guys, every of the concept I have explained in the whatever time I have got. Okay, obviously it's a one shot lecture, but I think if you are simply going through all of the points and all of the questions, you are going to get a very good confidence. Okay, And if you're going to give any examination, like very near, some of the very important examinations are present, so you should watch all of these important points, because everything I have covered with respect to the examination point of view, specifically the JEE mains, is present in this lecture. Obviously, NEET is easier portion. My all lectures, I have seen some of you are commenting that this lecture is of the JEE mains or the NEET. My all lectures are completely on the basis of the JEE mains. Okay, NEET is something you will automatically cover from that, but JEE mains is having somehow some more concepts, some more examples, and all these things. Okay, and thank you so much for attending the lecture.